Hello there, and welcome to Science for Sleep, where curiosity gets cozy and science takes the scenic route to slumber. Tonight's quiet journey takes us far from the warmth of our own sun into the dark stretches that lie between the solar systems of our galaxy. It's an odd thing to think about, isn't it? We spend so much time talking about stars, planets, and light, yet most of the Milky Way is made of the space between them, a sea of nearly nothing that somehow connects everything. I wonder where you're listening from tonight. Maybe you're under the same stars we'll soon wander between. Maybe you're wrapped in a blanket watching the slow dance of city lights through a window. Or maybe it's late, and you're somewhere quiet enough to imagine the sky stretching forever. Wherever you are, you're already part of this story. The atoms that make you were born in the very spaces we're about to drift through. If you find this calm or curious, or just a gentle way to wind down, I'd be grateful if you'd give the video a like or maybe subscribe. It helps this little corner of calm reach others who might need a soft place to land too. Now, take a slow breath, settle your thoughts, and let's begin. Between the stars lies a landscape that is neither empty nor still. It is the interstellar medium, the quiet ocean of gas and dust that fills the gaps between solar systems. Most people imagine outer space as a perfect void, a pure nothingness where not even dust dares to float. But that's only part of the story. The spaces between the stars are not empty, they're just incredibly thin. Imagine spreading a single grain of sand across a space the size of a football field. That's roughly how sparse the matter is out there. Yet even that faint scattering of atoms and particles holds the history of the galaxy. When you look up at the night sky, what you see are islands of brightness separated by vast darkness. But that darkness isn't an absence, it's a medium. Every photon that reaches your eyes has crossed those invisible seas. It's been bent, scattered, or softened by the faint gas and dust floating between solar systems. In some ways, the light we see from distant stars is a story about what lies between them. The interstellar medium, thin as it is, affects how light moves, how stars are born, and how galaxies evolve. Without it, there would be no stars at all. Let's imagine for a moment that you could drift freely beyond the edges of our solar system, past the outer planets, past the frozen Kuiper belt, past the Oort cloud where comets sleep in their long, slow orbits. Eventually you'd reach a boundary where the sun's influence fades, a bubble known as the heliosphere. Beyond that bubble lies true interstellar space, the domain of the galaxy itself. There, between one star and the next, you would find yourself surrounded by matter so thin you could travel billions of kilometers before colliding with a single atom. The density of hydrogen, the most common element in the universe, might be only 1 atom per cubic centimetre. In comparison, the air around you contains about 10 billion trillion molecules per cubic centimetre. The difference is almost impossible to grasp. Yet even in this vast emptiness, something stirs. That something is not silence in the ordinary sense. It's not the stillness of a room after everyone has left. It's more like the silence of deep water, full of hidden motion, pressure, and faint currents. There are clouds of hydrogen gas drifting between stars, some cold and quiet, others warm and ionized by the light of nearby suns. There are filaments of dust winding through space, reflecting starlight in soft, ghostly hues. There are shock waves from ancient supernovae rippling outward, shaping the material that will one day become new solar systems. Every part of this interstellar ocean is slowly changing, slowly moving, though its pace makes glacial motion look hurried by comparison. If you could watch this space in fast motion, sped up 1 billion times, you'd see patterns emerge, wisps of gas flowing toward regions of higher density, shock fronts colliding, giant clouds collapsing under their own gravity until they ignite, forming new stars. From afar it would look like breathing, the galaxy inhaling and exhaling across millions of years. But to our human sense of time, these motions are imperceptible. We see the stars as fixed points, but they are drifting through the interstellar sea, each surrounded by its own invisible bubble of plasma and magnetic field. The sun moves too, carrying its planets with it, weaving through the galactic medium like a ship through calm, endless water. The idea that there is something out there, even between the stars, changes how we think about emptiness. The interstellar medium may seem thin, but it is full of meaning. The elements that make up planets, oceans, and living things, carbon, oxygen, nitrogen, iron, were all forged inside stars and released into space when those stars died. Over millions of years, those elements mixed with the interstellar gas, spread by winds, collisions, and supernova explosions. They drifted through space until gravity gathered them again into new systems. Every breath you take carries atoms that once floated in that ancient galactic night. If you could trace one of those atoms, say a carbon atom in your body, back through time, you might find it was formed in the heart of a massive star long before the sun existed. When that star reached the end of its life, it exploded, scattering its contents across the galaxy. That carbon atom may have wandered through interstellar space for hundreds of millions of years, joining clouds, escaping them, carried by magnetic fields, before eventually settling into the gas cloud that gave birth to our solar system. Over billions of years, it found its way into Earth, into plants, into you. So even as you lie there now listening, your body carries the memory of what lies between solar systems. You are, in the most literal sense, made of the space between the stars. The distances between solar systems are enormous. Our nearest neighbour, the Alpha Centauri system, lies more than 4 light-years away. That's roughly 40 trillion kilometres. If the Sun were the size of a coin, Alpha Centauri would be another coin several thousand kilometres away, with only a few wandering atoms between them. It's easy to feel small in that context, but also strangely connected. Because despite the emptiness, those systems are linked by the same galactic environment. The dust that floats between them is shared material, shaped by the same forces, part of a single, slow-moving ecosystem on a cosmic scale. The temperature out there depends on what kind of interstellar region you're in. Some areas, near bright stars, can reach thousands of degrees. Others, in dark molecular clouds, hover just a few degrees above absolute zero. Yet even at those frigid extremes, chemical reactions can occur, albeit very slowly. Molecules like carbon monoxide, ammonia, and water vapour can form on the surfaces of dust grains. In time, those grains clump together, gathering mass, until they become the seeds of new stars and planets. So the emptiness between solar systems is not a void but a nursery, a place where the next generation of worlds is quietly forming. Radiation moves through these spaces too, shaping them in subtle ways. Cosmic rays, born from the violent end of massive stars, stream through the galaxy at nearly the speed of light. They collide with atoms in the interstellar gas, ionizing them, altering chemistry, sometimes even triggering new waves of star formation. These particles are invisible to the eye, but they're one of the ways the galaxy keeps itself alive, recycling energy from death into new beginnings. The spaces between solar systems are not passive, they're dynamic, humming quietly with the echoes of creation and destruction. If you could somehow drift through interstellar space, shielded from the radiation and cold, you would see faint shifting colours in the distance. Wisps of red and blue light from nebulae, the afterglow of ultraviolet radiation bouncing off dust. You might see dark patches too, regions where dust clouds are so thick they block the starlight behind them. These are often the birthplaces of new stars. From the outside they look like voids, but inside gravity is pulling material inward, compressing it until nuclear fusion begins. The darkness between stars hides a quiet kind of activity that only becomes visible when new light is born. Our sun is not alone in drifting through this ocean. It's currently moving through a region known as the local interstellar cloud, a thin pocket of gas and dust roughly 30 light-years across. Before that, it may have passed through denser regions, and in the far future it will move into others. These transitions can affect the outer boundary of the solar system, compressing or expanding the heliosphere. That means the conditions of interstellar space, its density, temperature and magnetic fields, can subtly influence the environment here on Earth, even across billions of kilometers. The edge of the galaxy is not some distant wall. It's all around us, gently brushing against the edges of our solar bubble. For all its thinness, interstellar space carries the fingerprints of countless events. Every supernova leaves behind shock waves that ripple through the surrounding medium. Every star emits stellar winds that push material outward. Over time, these forces carve bubbles, shells, and filaments in the galactic gas. The Milky Way, if you could see it without the glare of stars, would look like a complex web of glowing threads and empty pockets, a structure built by the combined breath of billions of suns. The space between solar systems is not random. It's sculpted, layered, full of quiet architecture. Astronomers study this invisible landscape using light in all its forms. Radio waves reveal cold hydrogen clouds. Infrared light shows where dust is warming near young stars. X-rays trace the hot ionized gas left by ancient explosions. Together, these observations let us map the unseen terrain between systems, a kind of galactic weather report. The patterns we find tell us where new stars will form, where old ones have died, and how material moves through the Milky Way. It's humbling to realize that what looks like empty darkness to our eyes is, in reality, the connective tissue of an entire galaxy. And within that tissue, tiny motions accumulate. A molecule here, a dust grain there, moving slowly, colliding, joining, drifting apart again. Over time, these small actions shape the future. The interstellar medium is patient. It doesn't hurry. It doesn't rush toward creation. It waits, quietly, until the right conditions arise. A passing shockwave, a gravitational nudge, a subtle imbalance. And then, at last, a cloud begins to collapse, forming the bright point of a new star. From that star, a new solar system will form, and one day, perhaps, another listener somewhere will look up and wonder what lies between. Out there, between the solar systems of our galaxy, the darkness isn't empty. It's a living canvas of atoms, radiation, and fields, all woven together in the slow dance of cosmic time. The journey between one star and the next may take tens of thousands of years, even at the speed of light. But in that distance lies the material that connects them. The dust, the gas, the magnetic threads, all part of a single continuous medium that makes the Milky Way more than a collection of stars. It makes it a whole. If you could drift endlessly away from the sun, further than the planets and comets, past the faint boundary of the heliosphere, you would find yourself surrounded by a darkness so deep that it seems to swallow thought itself. But this darkness isn't the kind that simply hides things. It's not an absence. It's a kind of quiet fullness, a place where light has travelled too far to remain bright, and where even the simplest forms of matter rest in slow motion. It is, in many ways, the ocean between stars, not made of water, but of time, distance, and the faint shimmer of scattered particles that never quite touch. People often imagine the space between solar systems as pure emptiness, a perfect vacuum where nothing at all exists. But emptiness is never truly empty. The darkness of interstellar space is more like a faint mist stretched impossibly thin, a mixture of atoms, dust, radiation, and invisible magnetic lines that drift quietly through the galaxy. It's a kind of substance that's almost not there, but still enough to shape how the Milky Way lives and breathes. If the galaxy were a living organism, these dark stretches would be its bloodstream, carrying materials, energy, and quiet messages from one luminous organ to another. If you were somehow suspended in this vast darkness, you wouldn't see much with your eyes. The nearest star would appear as a sharp pin of light, its glow barely piercing the black. There would be no horizon, No up or down, just an endless depth of nothing that seems to go on forever. But if your vision could stretch across all wavelengths of light, radio, infrared, ultraviolet, X-ray, the emptiness would begin to reveal its texture. You'd see faint threads of gas glowing gently, delicate filaments shaped by distant forces. You'd see patches of thicker dust where starlight dims and reddens, the marks of future star nurseries. Even in darkness there is movement, and even in silence there is structure. The vast majority of our galaxy is made up of this quiet material, what astronomers call the interstellar medium. It's not a uniform fog, but a complex, uneven mixture of regions that vary wildly in density and temperature. Some areas are filled with hot, ionized gas heated by nearby supernovae. Others are cold and dense where molecules cluster together and begin the first stages of new star formation. Between them stretch long corridors of nearly perfect vacuum. The result is a patchwork of extremes, fiery and frozen, dense and diffuse, luminous and invisible, all coexisting in a slow, perpetual motion. To understand how delicate this medium is, imagine holding out your hand and trying to catch the air around you. In that space, there are roughly 10 billion trillion molecules per cubic centimetre. In interstellar space, there might be one atom in the same volume, maybe two if you're lucky. It's so empty that you could travel hundreds of kilometres before bumping into a single hydrogen atom. Yet despite that sparseness, it's enough to scatter light, carry shock waves, and build the foundation of new worlds. On a cosmic scale, even the faintest traces of matter can add up to something enormous. Astronomers often describe interstellar space as being like an ocean, because it behaves that way over vast distances. There are currents, not of water, but of charged particles and magnetic energy. There are waves, shock fronts, and tides formed by supernova explosions, stellar winds, and gravity. These forces slowly push, pull, and sculpt the gas between stars into immense shapes. Giant clouds, filaments, and cavities that stretch for hundreds of light years. If you could see the Milky Way without its stars, you'd be left with something that looks like smoke frozen in time. A tangled web of dark and glowing threads suspended in a vast void. Light from distant stars travels through this medium, and along the way it changes. Some wavelengths are absorbed by gas atoms, leaving dark lines in the spectrum that astronomers can read like fingerprints. Other wavelengths are scattered by dust grains, giving distant starlight a faint reddish tint. This process, called interstellar reddening, is part of why some stars appear softer or dimmer than they truly are. It's the galaxy's way of reminding us that nothing travels untouched. Even the purest beam of light must pass through the quiet ocean and be shaped by it before it reaches another shore. If you could listen to this space, if somehow human hearing could translate electromagnetic whispers into sound, you'd hear a strange and constant hum. Not noise in the traditional sense, but a faint vibration. The combined murmur of particles colliding, fields shifting, and radiation moving through the dark. The Voyager spacecraft, now drifting beyond the edges of our solar system, have recorded faint plasma waves out there. These signals are evidence that space itself, even far from any star, is not dead. It resonates, softly and continuously, like the low breath of the galaxy. There's something humbling about realizing that even this apparent emptiness holds its own kind of weather. There are winds in interstellar space, streams of charged particles flowing from hot stars or blown outward by supernova remnants. These winds travel for thousands of light years, shaping the clouds they encounter, compressing them, sometimes triggering the birth of new stars. It's an almost poetic symmetry. The death of one star sending the raw materials for the next into motion. The ocean between solar systems is both a graveyard and a cradle, filled with traces of what was and hints of what will be. Scientists studying this darkness use every tool available to decode it. Radio telescopes detect hydrogen's faint emission at a wavelength of 21 centimetres. a soft glow that maps the invisible structure of the galaxy. Infrared observatories trace the warmth of dust clouds, where new stars are quietly forming. X-ray satellites peer into the hot, ionized gas that fills the spaces between large clouds, remnants of long-dead stars. Piece by piece, they've built a map of a world we cannot see directly, a world that makes up most of our galaxy's mass and defines how it evolves. Inside this dark expanse, every particle matters. A lone hydrogen atom drifting through space may, in time, join others, forming a molecule of hydrogen gas. That gas might collect in a cloud, cooled by dust grains that radiate away heat. As the cloud thickens, gravity begins to tug on it more strongly, and the temperature at its core rises. After millions of years, the pressure becomes so intense that nuclear fusion ignites. A new star is born. The light that eventually shines from that star will travel across the same medium that once sheltered its beginnings. What seems like a quiet void is, in truth, the breathing space of creation. The darkness between solar systems is so vast that human minds struggle to grasp it. If our sun were reduced to the size of a marble, the nearest star, Proxima Centauri, would be another marble placed more than 700 kilometers away. Between them, nothing solid, just that faint ocean of gas and dust, almost imperceptible yet everywhere, and scattered through that darkness are the memories of every star that has ever lived. Carbon, oxygen, silicon, iron. These elements drift together like ghostly plankton, waiting for the next tide of gravity to gather them into something new. The stillness of interstellar space is deceptive. It moves, but not in the way we do. It moves through pressure, temperature, radiation, and time. A shockwave from a distant explosion might take hundreds of thousands of years to cross a region. A molecule might spend 1,000,000 years slowly tumbling through cold space before colliding with another. Time flows differently there, not because of relativity, but because nothing hurries. It's a place where patience is the rule, and every motion is stretched thin across eternity. If you imagine the galaxy from afar, perhaps from some vantage point beyond its spiral arms, you'd see its light as a soft disk of faint shimmer. You might think that the darkness between the bright points is empty, but in truth, that's where most of the galaxy's story happens. It's where old stars give their matter back to space, and where new stars are gathering the pieces to form. It's where energy travels, dust circulates, and radiation finds its way. It's the connective tissue that keeps the galaxy alive. What makes this even more astonishing is how fragile it all is. The average density of the interstellar medium is so low that a small glass of air from Earth would contain more particles than a volume of interstellar space the size of a house. And yet, without that faint mist, no star could exist. It's a reminder that the grandest processes often begin with the smallest ingredients, atoms drifting in darkness, too subtle for us to see, yet capable of building everything. The darkness between solar systems also acts as a kind of memory field. Radiation from ancient supernova still echoes faintly through it. Dust grains carry isotopes that tell stories about where they formed and what kind of stars gave birth to them. By studying these traces, scientists can reconstruct the history of our galaxy, when stars lived, when they died, and how their remains were mixed into the next generation. It's a kind of archaeology, but instead of shovels and brushes, astronomers use light itself to uncover what's buried in the dark. Even our own solar system moves through this environment like a ship through invisible water. The sun's magnetic field forms a protective bubble called the heliosphere, which shields us from much of the galactic radiation. Outside that bubble, interstellar particles drift freely. Occasionally, a few make their way inside, interacting with the solar wind and leaving faint traces that our spacecraft can detect. Through those traces, we learn that the dark ocean outside is not static. It changes as the sun moves through it, as the galaxy itself shifts and flows. If you were floating there, In the darkness between solar systems, you might begin to lose your sense of scale. There are no landmarks, no boundaries, only the distant shimmer of stars. It would be easy to feel lost, but you'd also be surrounded by everything that connects those stars together. The dust that carries their remains, the gas that will feed their descendants, the faint magnetic threads that tie them into a single galactic web. You would be inside the structure that holds the Milky Way together. The darkness, instead of emptiness, would begin to feel like belonging. This space, this quiet ocean of darkness, is both the most desolate and the most fertile region of the cosmos. It's where nothing seems to happen and where everything begins. Every planet, every moon, every living thing started here, as part of this thin, drifting medium between stars. The silence of space isn't a void, it's a waiting room, a place where matter pauses between stories, where the next act of creation is gathering quietly out of sight. And so, when we look up at the night sky and see those points of light, it's worth remembering that most of what we're looking at isn't light at all. It's the dark in between, the vast, gentle ocean that fills almost everything. It's not empty. It's the space that holds the galaxy together, the space that gives birth to stars, the space that connects every atom we've ever known. The darkness between solar systems is not the absence of life or motion. It's the presence of possibility. If you could hold a piece of interstellar space in your hand, you wouldn't feel anything at all. No pressure, no texture, not even a hint of substance. You could reach out, close your fingers, and come away with nothing. That's because almost everything between solar systems is defined by absence. Not the absence of existence, but the absence of density. The thinness of everything out there is so profound that even words like vacuum fall short. We say space is empty, but the truth is far stranger. It's not empty in the way a room without furniture is empty. It's empty in the way a single breath of air spread across the distance between planets is empty. So empty that even the concept of emptiness starts to feel inadequate. The thinness of the interstellar medium is what makes it both invisible and essential. Most of the galaxy's volume is made up of this diffuse gas and dust, yet its density is almost beyond imagination. Here on Earth, air is heavy. Every breath presses on your skin with the weight of the atmosphere above you, a sea of molecules packed together in endless motion. In space, that pressure vanishes. Between stars, a cubic meter of space may contain only a handful of atoms. In some regions, there might be just one. The average density of the interstellar medium is about 1 atom per cubic centimetre, an amount so small that if you gathered all the matter in a cubic kilometre, you'd have less than a grain of dust. And yet that dust, that almost nothing, carries the ingredients of everything that will ever exist. If you could look closely enough at that 1 cubic centimetre, you'd find mostly hydrogen. It's the simplest, most abundant element in the universe, a proton with a single electron orbiting it. Mixed in, here and there, are helium atoms, remnants from the birth of the universe itself, and scattered among them are tiny traces of heavier elements: carbon, oxygen, nitrogen, silicon, iron, the ash of long-dead stars. Those atoms are few and far between, but they hold within them the entire story of cosmic evolution. They are the memory of what came before and the seed of what will come next. The interstellar medium isn't the same everywhere. In some regions, the gas is cold, dense and quiet, only a few dozen degrees above absolute zero. In others, it's hot and thin, energized by the blast waves of supernovae. This constant variation creates layers within the galaxy. The cold, neutral medium, where new stars form, the warm, ionized medium, where ultraviolet light from massive stars strips electrons from atoms, and the hot intercloud gas, where supernovae stir the mix into chaos. Each of these layers has its own texture, temperature, and purpose, like currents in an unseen ocean. Together they shape how galaxies evolve and how stars are born, live and die. But what does it mean for something to be this thin? It means that motion becomes slow. Collisions between atoms are rare events. A single hydrogen atom might travel for years, even centuries, before bumping into another. Heat, in the traditional sense, doesn't flow easily here. Instead, energy drifts across vast distances through radiation and magnetic fields. Pressure exists, but it's faint, like a whisper stretched across light years. To us, that seems like near nothingness, but to the galaxy, it's a delicate balance that keeps everything in motion. When astronomers measure this thinness, they don't just rely on counting atoms. They look at how light behaves as it moves through space. Certain wavelengths are absorbed by the gas, leaving dark lines in the spectrum of starlight. Those lines reveal what elements are present and how dense the space is between us and the star. By studying thousands of stars across the sky, scientists can map the invisible structure of the galaxy's interstellar gas, its filaments, bubbles, and voids. It's like tracing the veins of a leaf by watching how sunlight filters through it. The dust between stars is even rarer than the gas, but it has an outsized effect. For every 100 atoms of hydrogen, there's roughly one tiny dust grain. These grains are made of silicates, carbon compounds, ice, and metals. Most are smaller than a single bacterium, yet they're crucial to the galaxy's chemistry. Dust grains act as tiny laboratories where molecules can form, where hydrogen atoms meet and combine into H2, or where carbon and oxygen come together to form complex organic molecules. In the thinness of interstellar space, solid surfaces are scarce, so dust becomes the meeting ground for chemistry to happen. When starlight passes through dust, it's scattered and absorbed. Shorter wavelengths, blue and violet light, are more easily blocked, which is why distant stars appear redder than they are. The same process makes nebulae glow with soft colours, turning ordinary light into something dreamlike. The thinness of space makes light behave differently, stretching, dimming, and shifting as it travels. Over distances of thousands of light years, these small interactions add up, painting the galaxy in subtle shades that tell us what lies in between. The thinness also has another, more practical consequence. It allows stars to move freely. Each solar system drifts through this sparse medium without much resistance. The Sun, for instance, travels at about 230 kilometers per second around the center of the Milky Way. If the galaxy were filled with dense gas, that motion would slow down, drag would accumulate, and the stars would spiral inward. But because space is so incredibly thin, a star can glide through it for billions of years without losing momentum. The emptiness preserves motion, allowing galaxies to maintain their graceful rotation. Even so, the interstellar medium isn't entirely passive. When a supernova explodes, the blast wave sweeps up the surrounding gas, compressing it into dense shells. These expanding bubbles of energy carve out enormous cavities in the thin material, leaving behind what astronomers call superbubbles, regions tens or hundreds of light years wide filled with hot, ionized gas. Over time, these structures merge, forming a kind of frothy texture across the galaxy. The Sun itself currently drifts through one such region, a local bubble created by ancient supernovae long before our solar system formed. It's an invisible legacy of explosions that happened before Earth even existed. Inside that bubble, the thinness is extreme. The density of matter is lower than the already faint average of the galaxy. Yet even here, there are traces, a few atoms per cubic centimetre, a dust grain every few cubic metres. It's easy to overlook how extraordinary that is. Those scattered particles have been travelling for millions of years, shaped by radiation, twisted by magnetic fields, occasionally colliding, joining, or splitting apart. They've been everywhere, from the cores of dying stars to the outskirts of galactic arms. The thinness of everything means that motion never truly stops. It just slows until it becomes invisible to us. Temperature too takes on strange meaning in such a place. In everyday life, temperature is a measure of how fast atoms move and collide, but when collisions are rare, that definition begins to blur. The gas between stars can have temperatures of thousands, or even millions of degrees, but because the density is so low, it wouldn't feel hot. There aren't enough particles to transfer heat to your skin. It's like being surrounded by a warm wind that never actually touches you. Temperature, in the thinness of interstellar space, becomes more of a description of energy than of sensation. The thinness also affects time in subtle ways, not in the relativistic sense of Einstein's equations, but in how change unfolds. Processes that happen in seconds on Earth can take centuries in interstellar space. Chemical reactions proceed slowly because the participants almost never meet. Clouds of gas take millions of years to collapse into stars. Even light, the fastest thing there is, needs thousands of years to cross the vast distances between systems. The thinness stretches time until everything seems to move in slow motion. It's a place where patience is the only constant. Still, despite that patience, the interstellar medium is not static. It breathes. As stars form and die, they push material outward, which later cools and falls back in elsewhere. It's a galactic recycling system, slow but steady. Each generation of stars enriches the medium with heavier elements, and those elements in turn form planets, moons, and perhaps life. The thinness of everything makes that cycle possible. It allows material to travel freely, to spread and mix without clumping too quickly. It ensures that the galaxy remains dynamic and creative instead of collapsing into stillness. If you could watch the Milky Way over billions of years, you'd see the thin interstellar gas flowing like a tide between its spiral arms. You'd see supernovae flare, their shock waves spreading out like ripples on a pond. You'd see clouds forming, stars igniting, and then, eventually, those stars returning their material to the void. The galaxy would look like a single slow organism, breathing in and out, sustained by the thinness of its own substance. The space between solar systems, far from being dead, is the bloodstream that carries this slow rhythm forward. Our own solar system interacts with that thinness constantly. The solar wind, a stream of charged particles from the sun, pushes outward, carving a bubble in the interstellar gas. Where the solar wind meets the galactic medium, it forms a boundary called the heliopause. Beyond that, the sun's influence fades, and the true thinness of interstellar space begins. The Voyager probes crossed this boundary years ago, and their instruments confirmed what scientists had long suspected. Even out there, far from any star, there is still something. A whisper of particles, a trace of magnetism, the faint hum of the galaxy's plasma. When you think about the scale of it all, it's astonishing that such an environment could hold meaning for us. But it does, because everything we are began in that thinness. Every carbon atom in your body once drifted freely between stars. Every oxygen atom you breathe once existed in that invisible medium before it became part of a cloud, a star, a planet, a cell. The thinness of everything is not a void to be feared. It's the foundation from which all substance emerges. Without it, the universe would have no room to grow. So the next time you look at the night sky and see the stars hanging in darkness, remember that the darkness is not an absence. It's a structure so delicate that it defies imagination. A single hydrogen atom adrift in space may seem insignificant, but multiply it by the vastness of the galaxy, and it becomes a network connecting every star to every other. The thinness of everything is what holds the cosmos together. It allows light to travel, matter to move, and time to unfold. It's the invisible stage upon which every act of creation quietly takes place. The galaxy's beauty depends on its thinness. Too dense, and it would collapse into chaos. Too empty, and nothing could form. It's the balance between nothing and something that makes everything possible. Out there, between solar systems, that balance stretches endlessly, shaping the Milky Way's slow pulse, holding the stars apart just enough for life to happen, just enough for wonder to exist. And in that thought, the silence between worlds begins to feel not lonely but necessary. The thin breath of the universe, steady and eternal, waiting patiently between the stars. If the vastness between stars feels impossibly thin, then the dust within it is thinner still, yet more meaningful than almost anything else floating in the galaxy. It's strange to think that the foundations of planets, oceans and even life began as particles so small they can pass through a beam of light unnoticed. In the grand architecture of the cosmos, dust is both the debris and the blueprint. It drifts through space as if aimless, but every grain carries the story of destruction and creation woven together. The universe, in a way, builds everything out of its own ashes. Cosmic dust isn't the same as the dust on your shelf or under your bed, though the two share one thing in common. Both are evidence of things that used to be whole. On Earth, dust comes from what has decayed, disintegrated, or worn down with time. In space, the same is true. Dust forms from the remains of stars. When a star like our Sun reaches the end of its life, it sheds its outer layers into space. Those layers cool, condense, and eventually form microscopic grains. When a more massive star ends in a supernova, it forges heavy elements in its violent last moments, blasting them outward with immense force. Out of that explosion, dust begins to take shape. Tiny solid particles forged in fire and scattered across the galaxy. If you could see a single grain of cosmic dust up close, it would look nothing like the smooth, uniform particles we imagine. Most are jagged, irregular, a mix of silicates, carbon and metals clumped together in fragile forms. Some are crystalline, shaped by heat. Others are amorphous, shaped by cold. A single dust grain might measure less than a micrometer across, yet it can contain a complex internal structure, layers upon layers of elements accumulated over eons. Many carry traces of the stars they came from, isotopic signatures that reveal their birthplace. Scientists studying meteorites have found dust grains older than the solar system itself, tiny fossils of ancient stars that lived and died long before the sun was born. When dust first leaves its parent star, it doesn't stay still. Radiation pressure pushes it outward, carrying it into the interstellar medium. Over time, it mixes with gas, joining the slow current that drifts between solar systems. These grains wander for millions, sometimes billions of years. Along the way, they collect ice, react with ultraviolet light, and occasionally collide, sticking together or breaking apart. The dust is constantly being destroyed and remade. In dense molecular clouds, it helps shield delicate molecules from radiation, allowing chemistry to flourish. In more exposed regions, it's eroded by cosmic rays and ultraviolet light, returning to atoms that will someday form dust again. Even in the silence of deep space, everything recycles. It's easy to think of dust as insignificant, but without it, the galaxy would be lifeless. Dust grains act as cooling agents in gas clouds, radiating away heat and allowing matter to collapse under gravity. Without that cooling, the gas would remain too warm to condense into stars and planets. Dust is what allows the interstellar medium to take shape, to fragment, to give birth to new systems. You could say that stars depend on dust just as much as dust depends on stars. It's a feedback loop of cosmic proportions. Stars create dust when they die, and dust creates stars when it gathers again. The dust that floats between solar systems is also the reason we can't see the centre of our own galaxy with our eyes. The Milky Way's spiral arms are filled with thick lanes of interstellar dust that block visible light. Those dark streaks that run across the night sky aren't voids, they're clouds, dense enough to dim the starlight behind them. Yet when we look with infrared telescopes, the picture changes. Infrared light passes through dust more easily, revealing stars hidden within. These observations show that even the darkest patches of sky are crowded with activity. Behind the curtain of dust, stars are forming in secret. Inside these dark clouds, dust plays another role. It's a surface for chemistry to happen. When hydrogen atoms stick to a dust grain, they can combine to form molecular hydrogen, the most common molecule in the universe. This process can't happen easily in gas alone because the atoms need something to carry away excess energy. Dust grains act as tiny laboratories, providing surfaces for reactions and absorbing the leftover heat. Over time, more complex molecules form: carbon monoxide, ammonia, methanol, even simple organic compounds. Some of these molecules become the building blocks of life long before they ever reach a planet. In this way, dust is not just debris, it's a chemical catalyst, turning the thin gas between stars into something richer. When a new star begins to form inside one of these clouds, the dust around it starts to glow. The heat from the young star warms nearby grains, causing them to radiate in infrared light. What we see through telescopes are these glowing cocoons, faint but beautiful, like embers floating in a dark sea. Some of the dust will spiral into the forming star, adding to its mass. The rest will flatten into a disk around it, the beginnings of a planetary system. Inside that disk, dust grains collide and stick together, growing into pebbles, rocks, and eventually planets. The Earth itself began this way, as dust grains orbiting a young sun, clumping together over millions of years until they became something solid. Every mountain, every ocean, every cell can trace its ancestry to those drifting particles. Even after planets form, dust remains part of their story. Comets, asteroids, and meteorites carry pristine samples of interstellar dust that have survived since the earliest days of the solar system. Some of these grains still bear the isotopic fingerprints of the stars they came from. When we collect them and study their composition, we're holding pieces of the galaxy's memory. NASA's Stardust mission, for example, captured particles from a comet and returned them to Earth. Among them were grains older than the Sun, each one a tiny witness to billions of years of cosmic history. Dust also affects how galaxies evolve on a grand scale. It absorbs starlight and re-emits it as infrared radiation, redistributing energy throughout the galaxy. It helps regulate temperature and shields fragile molecules from destruction. When astronomers model how galaxies grow and change, dust is a crucial ingredient. Without it, the equations fail to reproduce what we see. The thinness of the interstellar medium and the faintness of dust might seem like minor details, but they determine how the universe behaves. The galaxy's brightness, its colour, its temperature, all are shaped by those invisible particles drifting through space. If you were somehow able to collect all the dust in the Milky Way and gather it into one place, it would still be a small fraction of the galaxy's total mass, maybe 1% give or take. Yet that 1% carries more significance than its quantity suggests. It's the source of planets, the shield of life, the fingerprint of time. The dust is what connects stars to the spaces between them, what records their deaths and prepares for their rebirth. It's fragile, transient, and yet utterly essential. Even now, dust is forming somewhere in the galaxy, perhaps in the cooling winds of a red giant star, where atoms condense into crystals as they drift away from their parent sun. Perhaps in the chaos of a supernova, where heavy elements coalesce as the shockwave expands into space. Every grain that forms is a message from the past, a physical memory of energy transformed into matter. And as those grains drift into the interstellar medium, they join a current that flows quietly through the galaxy, waiting to become something new. The next time you see sunlight streaming through your window, catching the motes of dust floating in the air, it's worth remembering that the same principle applies across the universe. What looks like emptiness is always holding something delicate, suspended in motion. Every grain of dust that catches the light is a tiny echo of the same process happening between stars. On Earth, it's easy to sweep dust away, to see it as unwanted, as clutter. But in the cosmos, dust is everything. It's the starting point of structure, the quiet residue of creation, and the promise of what comes next. There's a poetic truth hidden in the science, though not in rhythm or rhyme, but in the way the facts themselves connect. Dust is made when things end. Stars explode, planets erode, collisions scatter debris. Yet from that destruction comes the material for beginnings. Dust doesn't die with its star. It travels on, carrying memory in its atoms, waiting for the next chapter. The galaxy's thinness allows it to float freely, to mix, to find new homes. In that slow drift, the universe writes and rewrites itself endlessly. If you could follow a single dust grain through time, you'd find that it moves between many worlds. It might begin in a dying star's outer layers, carried outward by radiation until it reaches interstellar space. It might wander for eons, encountering clouds, magnetic waves, and cosmic rays. Eventually, it could find itself caught in the gravity of a forming system, pulled into a protoplanetary disk. There, it could become part of a planet, a moon, or a comet. It might fall into an atmosphere, dissolve in rain, or rest inside a rock. One day, that same grain could return to space, freed again by erosion, impact, or evaporation. The life of dust is cyclical, eternal in motion even when all else seems still. In our own solar system, the evidence of cosmic dust is everywhere. Every night as Earth moves through space, countless tiny particles burn up in the atmosphere, creating meteors. Most are no larger than grains of sand, yet each one is a fragment of interplanetary or interstellar dust. Some originated from comets, others from asteroids, and a few from beyond our solar system altogether. When they strike the upper atmosphere, they vaporize, leaving faint trails that briefly light the sky. Each one is a visitor from the cosmic sea, a speck that travelled millions of years before finding its end in a moment of brightness. Saturn's rings, too, tell a story of dust. They're composed mostly of ice, but among those icy fragments are traces of silicate and carbon dust, remnants of ancient collisions. The rings shimmer because of the same principle that makes interstellar dust glow in infrared, scattering light through countless tiny surfaces. When we look at those rings through telescopes, we're seeing dust in a state of motion and transformation, caught between stability and dispersal. It's a reminder that dust isn't static. It's always in flux, balancing between existence and disappearance. Even the faint glow that surrounds the solar system, known as the zodiacal light, comes from dust. Tiny particles scattered throughout the inner solar system reflect sunlight, creating a soft triangular shimmer visible just after sunset or before dawn. That glow is a bridge between our local neighbourhood and the galaxy beyond. It's the same dust, the same material that fills the spaces between stars, just caught in the warm light of our sun. The difference is only distance and scale. If you were to step back and look at the Milky Way as a whole, you'd see that dust outlines its shape. It collects in spiral arms, tracing the paths where stars form and die. It gathers in dense regions where new clusters are born. It absorbs and scatters light, shaping how the galaxy appears from afar. Without dust, the Milky Way would look stark and flat, all light and no depth. Dust gives it dimension. It gives it contrast, form and shadow. The very beauty of the night sky, its variation, its mystery, exists because of dust. And somewhere within that dust lies us. The carbon in your body, the silicon in your bones, the iron in your blood, all once part of interstellar dust. Those elements travelled across the galaxy before finding their way here. Every breath, every heartbeat, every thought depends on atoms that once drifted through that cosmic haze. The dust that dreams are made of is not a metaphor. It's a fact. The universe recycles itself through dust, and we are one of its outcomes. If there's comfort in that, it's because dust makes the universe feel connected. The spaces between solar systems might seem empty, but they're filled with the raw material of everything we know. Dust is the quiet thread that ties all worlds together, moving endlessly, reshaping, never ceasing to exist. It is fragile and persistent, fleeting and eternal, a paradox that defines the galaxy itself. And as we drift further into understanding what lies between the stars, dust is what reminds us that even in the thinnest, darkest reaches of space, creation is never truly over. It's simply waiting, quietly, patiently, suspended in the lightless ocean, carrying the ingredients of worlds yet to come. Between the stars, beyond the thin threads of dust, lies a substance even more elusive, the gas that fills the spaces of the galaxy. It moves quietly, unseen, and yet it is everywhere. This is the interstellar gas, the whispering medium through which light travels, through which stars are born and through which the galaxy breathes. It doesn't flow like air, and it doesn't move like wind. Its currents are so faint that entire worlds could drift through it for ages without noticing. But on the scale of the Milky Way, it is the hidden structure that connects everything. If dust gives the galaxy its texture, gas gives it its voice. The two exist together, inseparable but distinct, partners in a long, slow conversation between death and rebirth. Gas is the most abundant component of the interstellar medium, mainly hydrogen, with a smaller fraction of helium and traces of heavier elements like carbon, oxygen and nitrogen. It may seem too thin to matter, but its total mass rivals that of all the stars combined. Spread out, it forms a nearly invisible ocean that stretches across every corner of the Milky Way. The whispering nature of this gas comes from its incredible rarity. Imagine standing in a space so empty that the nearest atom is meters away. Now imagine that same emptiness extended over trillions of kilometers. That's what the gas between solar systems is like. In some regions, it's denser, a few hundred or thousand atoms per cubic centimeter. In others, it's almost completely void, with fewer than one atom per cubic centimeter. Yet even that faint whisper is enough to create structure. Over time, gravity, radiation and magnetism shape this gas into vast clouds that span light years, cold and still, waiting for something to disturb them. Astronomers classify the interstellar gas into different forms, each with its own personality, shaped by temperature, pressure and proximity to stars. There's the cold, neutral medium, where hydrogen atoms drift quietly in darkness, sometimes forming molecules. There's the warm, neutral medium, slightly hotter, more diffuse, where gas glows faintly in ultraviolet light. Then there's the warm ionized medium, where starlight has stripped electrons from atoms, leaving a faint plasma that fills much of the galactic disk. And beyond these, in the cavities carved by supernovae, lies the hot ionized medium, gas so rarefied and energetic that it glows in X-rays. These forms flow together, blending at the edges, constantly changing as stars form and die. If you could see hydrogen in visible light, the galaxy would look nothing like the one we know. Instead of sharp stars against a dark background, you'd see filaments and wisps of faint red glow, a web of hydrogen gas stretching between systems. Astronomers can observe this glow at a specific wavelength, 21 centimeters, produced by a quantum flip in the hydrogen atom's electron. This emission line is one of the most important tools in astrophysics. By mapping it, scientists can trace the motion of gas throughout the Milky Way, measuring how it rotates and where it gathers. In radio images, the galaxy reveals itself not as a cluster of stars, but as a vast network of flowing hydrogen clouds. These clouds are far from uniform. Some are diffuse and spread thinly across thousands of light years. Others, known as molecular clouds, are dense enough for hydrogen atoms to bind together into molecules. These molecular regions are the birthplaces of stars. Inside them, the gas cools to temperatures near absolute zero, and gravity begins to pull it inward. Over millions of years, the gas collapses into dense knots that grow hotter and denser until nuclear fusion ignites. From the outside, these clouds look like shadows, dark nebulae that block the light of stars behind them. But inside, new suns are forming quietly, fed by the whispering gas that drifts around them. The most famous of these regions can be seen even with small telescopes. The Orion Nebula, for example, is a bright cloud of ionized gas about 300 light-years away. What we see as a glowing patch of pink and blue is hydrogen gas energized by young stars at its core. Their intense ultraviolet radiation strips electrons from hydrogen atoms, and when those electrons recombine, they emit light. The result is a faint luminous fog, the visible breath of the galaxy. In a sense, every glowing nebula is the sound of the interstellar gas speaking in light, a whisper made visible. But not all of the gas is warm or bright. Most of it is cold and invisible, detectable only by the way it absorbs or emits radio waves. Some clouds are so dark that they block nearly all background starlight. Others are so faint that they can only be found indirectly, through their effect on nearby light. These hidden regions make up a large part of the Milky Way's mass. They're like the deep currents beneath an ocean's surface, unseen but essential for everything that happens above. The whispering nature of the interstellar gas is not only about its faintness, but also about how it moves. Unlike the air around us, which flows freely and predictably, interstellar gas is tied to magnetic fields that crisscross the galaxy. Charged particles spiral along these invisible lines, forming filaments that can stretch for hundreds of light years. When shock waves from supernovae pass through, they twist and compress these magnetic structures, shaping new clouds in the process. The result is a galaxy filled with patterns too slow for us to see, but too intricate to be random. Inside molecular clouds, the gas behaves differently. There, atoms and molecules are packed close enough to interact, though still unimaginably far apart by earthly standards. Temperatures drop to around 10 degrees above absolute zero. In that cold, chemical reactions slow to a crawl, but they don't stop. Molecules like carbon monoxide, ammonia, and formaldehyde form, clinging to dust grains that float within the gas. These molecules emit faint radio signals, which astronomers detect to map the structure of cold clouds. The signals are so weak that they often take hours or days to capture, but together they reveal an extraordinary picture, a hidden architecture of gas and chemistry stretching across the galaxy. When enough gas collects in one place, something remarkable begins to happen. Gravity starts to take over, pulling material inward. As the cloud collapses, it fragments into smaller cores, each destined to become a star. The pressure and heat in those cores rise until hydrogen begins to fuse into helium, releasing energy. The young star ignites, sending radiation streaming outward. That radiation pushes away much of the surrounding gas, carving out cavities and blowing material into space. The balance between collapse and expansion defines the life of the galaxy. Where gas gathers, stars are born. Where stars shine, gas disperses. It's an endless, slow rhythm. Inhale, exhale. The galaxy breathing in hydrogen and breathing out light. The energy of massive stars has an especially strong effect on the interstellar gas. Their radiation ionizes nearby hydrogen, creating regions known as H2 regions, pockets of glowing plasma that mark places where new stars have recently formed. These regions expand over time, merging with others, forming bubbles and shells that spread through the interstellar medium. Eventually, the stars at the center exhaust their fuel and explode as supernovae, sending shock waves that compress nearby gas, starting the process all over again. The galaxy, through its gas, maintains a kind of equilibrium. Destruction feeding creation, silence giving way to sound. Even outside the spiral arms, where star formation is rare, the whispering gas continues to drift. In the galactic halo, far above the plane of the Milky Way, thin streams of hydrogen flow between regions. Some of this gas falls slowly toward the disk, replenishing the material needed for future generations of stars. Some escapes entirely, carried away by stellar winds and supernova-driven outflows. The boundaries between the galaxy and intergalactic space are soft, blurred by this exchange. What lies between solar systems is connected not just within the Milky Way, but to the spaces beyond it, a continuous network of gas stretching across the universe. It's strange to realize that even though we can't see this gas, we depend on it completely. The sun, the planets, the Earth, and everything alive upon it came from a cloud of whispering gas billions of years ago. Every breath you take contains atoms that were once part of that diffuse medium. The oxygen you breathe and the hydrogen in every drop of water were both born in the same cycle. Gas-forming stars, stars creating heavier elements, those elements returning to gas and gas-forming stars again. The galaxy is not just a collection of suns, it is a single system of circulation, a continuous transformation of hydrogen into complexity. In some ways, studying interstellar gas is like listening for a sound too soft to hear directly. Astronomers must rely on echoes, on the way light is absorbed, on the faint emissions that trace its presence. They build maps from signals measured in microwatts, assemble images from photons that have travelled for centuries. The result is a picture not of emptiness, but of motion, subtle, constant, intricate. Every region of the Milky Way is connected by these streams of gas flowing quietly between solar systems, carrying the dust and elements that form everything we know. If we could somehow compress all that gas into a single sphere, it would still be smaller than the galaxy's stars combined. Yet without it, no stars could exist. The whispering gas is the raw material of creation, the canvas on which gravity and energy paint the patterns of the universe. It's a paradox of abundance in scarcity. There is so little of it in any one place, yet so much of it overall that it defines the structure of the galaxy itself. The thinness allows for freedom. The emptiness allows for life. Out there, in the vast quiet between solar systems, a single hydrogen atom can drift for millions of years before joining another. When it does, that meeting can set in motion a chain of events leading to the birth of a new star. From such small beginnings, light returns to the universe. The gas doesn't shout its presence, it whispers patiently, persistently. And through those whispers the galaxy endures. So when we look up at the stars, what we see are not just points of light, but the culmination of that invisible conversation, the quiet gatherings of gas that became suns, the faint traces of atoms that once drifted through the dark and now burn with brilliance. Every solar system is an echo of that process, a translation of whispers into radiance. The spaces between stars may seem silent, but in truth, they are filled with the softest, longest dialogue the universe has ever known. And somewhere in that dialogue, perhaps still unformed, perhaps already underway, are the beginnings of the next generation of stars. The gas is already gathering, already cooling, already preparing. The story doesn't stop. It never does. The whispering gas flows on, carrying with it the memory of everything that ever was and everything that will be, weaving the spaces between solar systems into one continuous, endless breath. If you could peel back the layers of darkness between stars beneath the dust and the drifting hydrogen gas, you would find something unseen but powerful threading through it all. Lines of invisible force that never rest, never vanish, never stop moving. These are the magnetic fields of the galaxy, vast and delicate, shaping matter without ever touching it. They stretch between solar systems like rivers made of influence, bending the paths of charged particles, guiding clouds of gas, and defining how energy flows through the Milky Way. They are not seen, but their presence is everywhere, quiet and constant, like the steady pulse beneath the surface of a calm ocean. The idea that empty space can hold magnetism is easy to overlook because we rarely sense it directly. On Earth, we're surrounded by the planet's own magnetic field, but it's gentle and stable, a shield that protects us from the solar wind. Out in the galaxy, there's no single dominant field. Instead, there are countless threads of magnetism woven together, twisting and curving through interstellar space. They form an enormous interlocking web that links stars, dust, and gas into a coherent whole. The field lines don't exist independently of matter. They interact with it, move with it, and shape its evolution. The galaxy's magnetic structure is one of the quietest forces in existence, yet it plays a role in almost every process that happens between solar systems. Astronomers call this vast system the galactic magnetic field. It runs through the disk of the Milky Way and extends far into the surrounding halo. It's weak, much weaker than the magnetic field of a refrigerator magnet, but it acts over such large distances that its influence becomes enormous. The field is typically a few microgauss in strength, far too faint to affect a human body, but enough to steer the motion of charged particles across light years of space. It threads through the interstellar gas like an invisible current, shaping how that gas flows and how it clumps into clouds. Without it, the Milky Way would look very different. The magnetic field lines follow the spiral arms of the galaxy, curving gracefully around its core. Within those arms, the field weaves in and out of dense clouds, sometimes aligning with them, sometimes twisting at odd angles. Observations show that the magnetic lines are not smooth but tangled, braided by turbulence and shock waves from supernova. The field shifts as energy moves through it, creating loops, knots, and filaments. In some regions, it runs parallel to the galactic plane. In others, it extends vertically, connecting the disk to the halo. The result is a structure both ordered and chaotic, a balance between symmetry and disturbance that reflects the living state of the galaxy itself. One way scientists study these magnetic rivers is through the light that passes through them. As polarized light travels through a magnetized plasma, its plane of polarization rotates, a phenomenon known as Faraday rotation. By measuring how much that rotation changes across different wavelengths, astronomers can infer the strength and direction of the magnetic field along the line of sight. Another method uses the alignment of dust grains. Many interstellar dust particles are slightly elongated, and they tend to spin in response to magnetic fields, aligning themselves like tiny compasses. When starlight scatters off these aligned grains, it becomes polarized in specific patterns. By mapping this polarization across the sky, scientists can trace the invisible threads of the galactic field. These observations reveal that magnetism doesn't just exist alongside matter, it shapes it directly. In molecular clouds where stars are born, magnetic fields resist gravity's pull. They slow down the collapse of gas, guiding it into filaments and channels. Without that resistance, clouds might collapse too quickly, forming too many stars too fast. The field acts like a subtle regulator, keeping star formation balanced over cosmic time. It also influences the direction of outflows and jets from young stars, focusing them along magnetic lines. Even at the smallest scales, the invisible force of magnetism leaves fingerprints on everything it touches. It's easy to imagine the magnetic field as static, frozen in place, but it's not. The movement of charged particles through the interstellar medium continuously shapes and strengthens it. This process, known as the galactic dynamo, converts kinetic energy from gas motion into magnetic energy. As the Milky Way rotates, the swirling gas drags magnetic lines with it, stretching and twisting them. Over time, this motion amplifies the field, maintaining its strength and structure. In this sense, the galaxy's magnetic field is alive, constantly renewed by the very matter it influences. These rivers of magnetism also guide some of the most energetic travelers in the universe, cosmic rays. These are high-energy particles as mostly protons and atomic nuclei. accelerated by supernova explosions, black holes, and other violent events. As they move through the galaxy, they don't travel in straight lines. Instead, they spiral along magnetic field lines, bouncing and scattering as they go. The field confines them, trapping them in the Milky Way for millions of years. It's because of this confinement that we can detect cosmic rays at all. Without the galactic magnetic field, most of them would escape into intergalactic space before ever reaching us. The presence of magnetic fields even affects how light itself moves. In strong magnetic environments, radiation can be polarized or absorbed differently depending on its direction relative to the field. This means that indirectly, magnetism can shape how we see the universe. When we observe distant regions of the Milky Way, we're not just seeing the stars and gas. We're seeing light that has passed through a complex lattice of magnetic forces, altered slightly by every encounter. It's as if every photon carries a record of the invisible rivers it once crossed. What's remarkable is how these faint fields manage to remain coherent over such enormous scales. A single magnetic line might extend for hundreds of light years, maintaining its direction even through turbulent regions. The reason lies in how the field and the gas interact. The charged particles within the gas move along magnetic lines, but they also generate currents that reinforce those same lines. The two systems feed into each other, locking together in a dynamic equilibrium. If one shifts, the other responds. The result is a kind of stability through constant motion, a network of influence held together not by strength, but by continuity. On smaller scales, these fields shape individual solar systems. The Sun's own magnetic field is carried outward by the solar wind, forming a bubble around our system known as the heliosphere. At the boundary where the solar wind meets the interstellar magnetic field, the two press against each other, distorting and blending. Voyager 1 and 2, the spacecraft now drifting beyond this boundary, have recorded subtle changes in particle flow that reveal how the local galactic field interacts with the Sun's. These measurements show that magnetism is not an abstract concept, but a real, physical texture of space, something that can be felt, measured, and crossed. When a star dies, the magnetic story continues. Supernovae don't just release energy, they also compress and distort magnetic fields. The shock waves amplify the fields within the expanding debris, creating localized regions of intense magnetism. These areas can accelerate particles to near-light speed, feeding the galaxy's supply of cosmic rays. Over time, the remnants of these explosions merge with the surrounding medium, spreading magnetized gas across the spiral arms. The galaxy, through cycles of life and death, renews its magnetic structure the same way it renews its stars and dust. Even in the vast, sparse regions between solar systems, magnetism leaves its mark. Charged particles moving along the field lines create faint currents, which in turn generate low-frequency radio waves. These waves ripple through the interstellar medium, carrying information about the field's orientation and strength. Instruments sensitive enough to detect them can, in theory, map the invisible motion of space itself. Though we can't yet listen to these signals directly, their presence is a reminder that the quiet between stars is filled with motion too subtle for human senses. The magnetic field also plays a role in shaping the large-scale structure of the Milky Way. It helps define the boundaries of the spiral arms, stabilizing them against collapse. It influences how gas flows into the galactic center, where the supermassive black hole resides. It even affects how matter moves in the halo, slowing the escape of gas into intergalactic space. Without these fields, the Milky Way's disk might have fragmented long ago. Magnetism gives the galaxy its form, its resilience, and its internal balance. For decades, astronomers struggled to visualize these invisible forces. Recently, using data from satellites and radio telescopes, they've begun to build three-dimensional models of the galactic magnetic field. These models reveal complex patterns, arcs, loops, and threads that twist through space like strands of fiber optics. Some regions show tightly wound filaments, while others reveal broad, sweeping curves that span entire spiral arms. Together, they form something that looks almost organic, a system of branching veins and arteries through which energy flows continuously. When viewed at this scale, the galaxy appears less like a collection of stars and more like a living structure sustained by magnetism and motion. The influence of magnetic fields extends even further than we once believed. Observations of other galaxies show similar patterns, spiral magnetic lines that mirror their optical structures. Even in intergalactic space, far beyond the reach of stars, weak magnetic fields appear to exist, connecting galaxies across cosmic filaments. This suggests that magnetism might be a fundamental property of the universe, present from its earliest moments. Some theories propose that the first magnetic seeds were born in the primordial plasma shortly after the Big Bang. Over billions of years, those seeds were amplified by motion, turbulence, and the growth of galaxies, eventually forming the vast systems we see today. In a way, magnetism is the quiet architect of the cosmos. It doesn't shout or blaze. It shapes things gently, invisibly, through alignment and resistance. It holds together plasma that would otherwise scatter. It directs radiation, and it organizes chaos into patterns. Every cloud of gas, every spiral arm, every glowing nebula owes part of its form to these unseen rivers, and though we can't feel them, we're part of them too. The magnetic field of the galaxy flows through the solar system past the planets, past the Earth, threading through every space between. It's a constant reminder that even in emptiness, there is connection. If you could somehow see those lines made visible, you might notice that they shimmer faintly, like threads in a vast tapestry. They would twist around stars, loop through dust clouds, and merge into the galactic plane before stretching outward into the dark. Each line would represent not just direction, but history. The record of how energy has moved through space over millions of years. Where lines converge, clouds form. Where they break, new fields emerge. The entire galaxy would appear to breathe, its magnetism flowing like blood through an unseen circulatory system. The rivers of magnetism carry no sound, no colour, no tangible presence. Yet everything that exists between the stars depends on them. They guide the motion of particles, regulate the birth of stars, and connect distant regions of the galaxy in subtle ways. The interstellar medium, with all its thinness and dust and gas, would drift without purpose if not for these magnetic currents steering it. They are the silent engineers of structure, the unseen symmetry behind the chaos of light and shadow. And as the galaxy continues its slow rotation, these fields turn with it, looping endlessly, weaving new patterns across the void. Every rotation, every ripple, every flare from a distant star sends a small disturbance through the web, a message passed along magnetic lines. These ripples might take thousands of years to cross from one arm to another, but they never truly fade. The magnetic field remembers, storing echoes of motion the way the ocean remembers waves. It's not an empty stillness out there. It's a calm filled with invisible movement, steady, constant, unending. If the dust and gas of the Milky Way are the matter of its body, then magnetism is its circulation, the quiet flow that holds everything in balance. It moves without resistance, invisible but indispensable, the binding fabric that keeps the galaxy whole. Out there, between solar systems, these magnetic rivers continue to flow, connecting everything in silence, carrying with them the imprint of stars, the memory of explosions, and the slow pulse of the Milky Way's eternal motion. Light has always been our way of seeing the universe. Every star, every planet, every distant galaxy speaks to us through the thin stream of photons that travel across the dark. But between those sources and our eyes lies a vast and complex space, a space that bends, scatters, and dims the light that passes through it. Much of that light never reaches us. It fades, absorbed by dust, deflected by gas, or stretched until its energy becomes something else entirely. What we see when we look at the night sky is only a fraction of what truly exists. The rest is hidden, moving silently through the dark light that never quite arrives. In the emptiness between solar systems, light travels freely but not untouched. The interstellar medium, thin though it is, interacts with every photon that crosses it. A single dust grain can absorb light, turning it into warmth and re-emitting it as faint infrared radiation. Clouds of gas can scatter light, changing its colour and direction. Some wavelengths are blocked entirely, leaving gaps in the spectrum that astronomers must interpret like missing pages in a book. The darkness between stars is not pure absence. It's a filter, constantly reshaping what passes through it. When light leaves a star, it begins a journey that can last for thousands or millions of years. Along the way, it crosses regions of varying density and composition. In one part of space, it might move through ionized hydrogen, its path slightly bent by magnetic fields. In another, it might pass through dense molecular clouds, losing energy as dust absorbs and re-radiates it. By the time that light reaches another star system or a telescope on Earth, it carries with it a record of everything it has encountered. The faint signatures of gas clouds, the fingerprints of atoms, the scars of distance itself. This gradual fading and transformation of the light is called extinction. It's one of the quietest processes in the universe, but it shapes how we perceive almost everything beyond our own solar system. The interstellar medium dims and reddens starlight, making distant stars appear older or cooler than they really are. Astronomers must correct for this effect to understand what they're seeing, using complex models of dust distribution and density. Even then, some light is lost forever, absorbed and re-radiated in directions we'll never detect. The galaxy's glow, as beautiful as it seems, is built upon countless photons that never reach their destination. The journey of light isn't always straightforward. Space itself bends it. Massive objects like stars, planets, and black holes warp the fabric of space-time, causing light to curve around them. This bending, known as gravitational lensing, can magnify or distort the images of distant objects. Sometimes it reveals things that would otherwise be invisible. Other times, it hides them behind layers of warped geometry. Even between solar systems, this effect subtly alters the paths of photons, changing the precise timing and direction of their arrival. The result is a universe that we see only partially, a version filtered through matter, gravity, and time. If you could somehow follow a single photon from its birth to its end, you would see an unbroken line through the galaxy, weaving between clouds and magnetic fields, crossing vast regions of near emptiness. You'd see it scattered occasionally, nudged by an atom or dust grain, its wavelength stretching as it loses energy. Over light years, those small effects accumulate. Some photons slow to infrared, invisible to our eyes but still carrying warmth. Others stretch further still into radio waves, their once bright energy now faint vibrations drifting endlessly through the interstellar medium. And many more are stopped entirely, absorbed by dust that re-emits them as a soft, diffuse glow. That re-emission is one reason the galaxy shines in infrared. Dust absorbs visible light, but it doesn't destroy it. It transforms it. The energy is released again, but at longer wavelengths, invisible to us. When astronomers use infrared telescopes to look at the Milky Way, they see a completely different picture than the one visible to our eyes. The spiral arms glow softly with thermal radiation from dust grains warmed by starlight. The darkest regions in optical images, where dust seems to swallow all light, become bright and structured in infrared. It's a reminder that darkness doesn't always mean absence. Sometimes it's simply a different kind of light waiting to be seen. The same principle extends to even longer wavelengths. Radio waves, for instance, pass through dust almost unhindered. They allow us to peer into places where visible light can't go, the centres of galaxies, the depths of molecular clouds, the regions where stars are forming. Every frequency of light reveals a different layer of reality. Visible light shows us stars, infrared shows us dust, radio shows us gas, X-rays show us hot plasma. The light that never arrives in one form often arrives in another, shifted and reshaped by its long journey through the interstellar medium. But there are limits. Some light is lost completely, scattered into directions where no receiver waits. Photons absorbed by dust are re-emitted randomly, their original paths forgotten. Others fall into black holes, trapped forever. And some are stretched so far by the expansion of space that their wavelengths exceed the size of the detectors we build. In that sense, the universe hides itself as much as it reveals itself. The stars we see are only the visible surface of something far larger and more intricate, a structure made of both illumination and concealment. The light we do see from distant stars carries more information than brightness alone. Within it are subtle lines and shifts that tell us about the composition, motion, and age of the source. Each atom leaves a signature, a specific set of wavelengths absorbed or emitted. By studying those lines, astronomers can determine what elements a star contains, how fast it's moving, and even how the gas around it behaves. Yet all of this information arrives altered by the medium in between. The light we analyze is not pure. It's filtered through a vast, whispering web of dust and gas, changed just enough to remind us that it travelled a long way to get here. Even within our own galaxy, this effect varies from place to place. In some directions, light travels almost unobstructed for thousands of light years. In others, a single dense cloud can block nearly everything behind it. These differences give the Milky Way its mottled appearance, bright clusters and dark rifts, glowing regions surrounded by shadows. The structure we see in the night sky is a map of where light succeeds and where it fails, a pattern drawn by the interplay between stars and the medium that surrounds them. There's something quietly profound about the idea that most of the light in the galaxy never reaches us. It continues its journey indefinitely, spreading thinner with distance, fading until it becomes indistinguishable from the background glow of space. Some photons will travel forever, never striking another particle or planet. They'll wander through the galactic halo, through the spaces between galaxies until their energy dissipates entirely. Light, for all its speed and brilliance, is fragile when stretched across cosmic time. The darkness we see isn't just the absence of light, it's the accumulation of all the light that has gone too far, spread too thin to be seen. When we look at the Milky Way from within, we're looking through layers of that lost light. Each faint haze, each dim streak, each soft shimmer is the visible remainder of something much larger. The galaxy glows not because of its stars alone, but because of the countless photons scattered by dust, reflected off gas, and absorbed before they could leave. It's a subtle brightness, one that fills even the darkest parts of the sky when viewed with sensitive enough instruments. The night, for all its stillness, is never truly black. The same process happens on smaller scales too. Within our solar system, sunlight reflects off dust particles and faintly illuminates the space between planets. That glow, called the zodiacal light, is a local echo of the same effect happening throughout the galaxy. It's the visible sign of light that doesn't make it all the way, caught and scattered before it can escape. Even here, in the familiar space around our sun, the story of light's transformation continues. Every beam we see is both arrival and remainder, a record of what was lost along the way. The limits of light define what we can know. We observe the universe not as it is, but as it appears through the thin veil of what blocks or alters illumination. The densest regions of interstellar space, where stars are forming deep inside molecular clouds, are hidden behind thick curtains of dust. We can't see them directly with optical telescopes. We can only infer their presence through indirect light, or by switching to infrared and radio frequencies. Even then, the picture remains incomplete. There will always be places where light cannot go, where darkness keeps its secrets for millions of years. Some of that hidden light reappears in ways we don't expect. The cosmic microwave background, for example, is light from the early universe stretched by expansion into long microwaves. It's everywhere, filling all of space, a faint echo of a time when light first became free to travel. Though it doesn't belong to any particular star or galaxy, it's part of the same story. Light that once blazed brightly and now whispers softly across the cosmos. Every photon we detect is part of that ancient exchange, part of the long conversation between matter and radiation that began billions of years ago. Even as light fades or vanishes, it leaves traces. Dust warmed by absorbed photons re-emits infrared radiation that tells us where the hidden stars are. Scattered light changes the polarization of the sky, revealing the structure of the gas it passed through. Absorption lines in spectra show us where clouds lie along a given path. By piecing together all these clues, astronomers can reconstruct what the naked eye cannot see, the full complexity of the galaxy's invisible spaces. In that way, even the light that never arrives continues to speak, indirectly but persistently. To understand this process deeply is to realize how much of the universe we will never see directly. For every star visible in the night sky, countless others are hidden behind dust or distance. For every photon that reaches a telescope, many more are lost along the way. Yet the patterns of what is missing are as informative as what remains. The absence itself becomes data. The galaxy, in its silence and shadow, tells its story through both illumination and loss. Light, after all, is not permanent. It is energy in motion, always changing form. When it's absorbed by matter, it becomes heat. When it's scattered, it becomes diffuse. When it's stretched by the expansion of space, it fades into background radiation. But none of it truly disappears. It transforms endlessly into new expressions. The light that never arrives is not wasted. It's redistributed, shared among dust grains, gas clouds, and magnetic fields. It continues the cycle of energy that sustains the galaxy, just beyond the limits of our perception. And somewhere out there, between the solar systems of the Milky Way, new photons are being born. Every second, stars ignite, flares burst, and atoms emit light as electrons fall into lower states. Those photons begin their journey through the same intricate web, some destined to travel freely, others soon to be scattered, absorbed, or lost. The balance never changes. The darkness and the light coexist, each shaping the other, each defining what the galaxy is. The night sky, as calm as it appears, is an ongoing record of that exchange. Every faint star, every patch of dim glow, every invisible wavelength carries the story of what the interstellar medium allows and what it withholds. The light that never arrives isn't gone, it's simply elsewhere, transformed into the warmth of dust, the hum of radiation, the faint background that fills the spaces between worlds. In that unseen glow, the galaxy keeps its quiet continuity, a conversation that never ends, a brightness that never truly fades, only changes form as it moves endlessly through the dark. If you could drift far enough into the darkness between stars, away from all warmth and motion, you would eventually reach places where even time feels like it has slowed to a crawl. Here, in the deepest regions of the interstellar medium, atoms move so slowly that their collisions are rare events, separated by centuries of quiet drifting. This is the long sleep of atoms, the suspended stillness that fills most of the galaxy. It's not death, and it's not emptiness. It's a kind of waiting, the slow heartbeat of the universe when nothing is in a hurry to change. Every atom, even when cold and still, carries energy. But in the vast darkness between solar systems, that energy is almost perfectly balanced. The temperature in these regions can fall close to absolute zero, just a few degrees above it. At such temperatures, motion slows to nearly nothing. Hydrogen atoms, the most common inhabitants of this space, drift at speeds of only a few hundred meters per second, a lazy stroll compared to the frenetic pace of atoms in air or water. Collisions between them happen rarely enough that, for all practical purposes, they move alone. Imagine being suspended in that stillness. No breeze, no sound, no gravity strong enough to pull you anywhere quickly. Just a faint scattering of atoms, each one carrying its own small history. Some of those atoms were born in the heart of long-dead stars, thrown into space by supernova explosions. Others have wandered the galaxy since its beginning, remnants of the hydrogen that filled the young universe before the first stars were born. They've been heated, cooled, ionized, and recombined countless times, and now they rest here, drifting in the thin plasma that connects everything, each one waiting for another encounter that might take centuries to come. Even in this deep cold, there is activity, slow, measured, almost imperceptible. Radiation still passes through, though faintly. Occasionally a cosmic ray or high-energy photon collides with an atom, ionizing it, stripping away an electron. The electron drifts for a time before reuniting with another atom, releasing a faint photon. That light is too weak for human eyes to detect, but it's enough for astronomers' instruments to register. Through these faint emissions, we learn that even the most silent regions of the galaxy are never truly still. Hydrogen dominates this frozen expanse, and its simplicity hides complexity. When two hydrogen atoms meet under the right conditions, they can form molecular hydrogen, H2. This molecule is the foundation of star formation, but creating it in the long sleep of atoms takes time. The atoms must first stick to the surface of a dust grain, find each other, and bond. In the cold and darkness, such meetings are rare. But the galaxy is patient. Over millions of years, enough molecular hydrogen forms to make clouds dense enough to collapse under gravity. What begins as stillness becomes the starting point for motion. In the colder regions of molecular clouds, temperatures drop to just 10 degrees above absolute zero. Here, the atoms truly rest. The gas is dense enough that the occasional collision transfers small amounts of energy, but the overall pace remains glacial. Chemistry continues, though slowly. Molecules form and freeze onto dust grains, building thin layers of ice. Carbon monoxide, water, ammonia, and other compounds accumulate. These icy mantles are fragile, destroyed easily by ultraviolet light, but within the darkness they endure. When a new star eventually forms nearby, its heat will evaporate them, releasing their stored molecules back into space. The end of one long sleep and the beginning of another cycle. The interstellar medium is a place of balance between movement and stillness, creation and waiting. The long sleep of atoms ensures that the galaxy doesn't burn itself out too quickly. If everything happened at once, if every cloud collapsed immediately, if every atom fused into heavier elements without pause, the Milky Way would have flared and faded long ago. Instead, the thinness of space and the slowness of these atoms stretch time, spreading creation across billions of years. What feels like inactivity is actually preservation. The universe keeps itself alive through restraint. When astronomers observe these cold regions, they rely on radio and infrared telescopes. Visible light cannot penetrate the darkness, but radio waves can. Certain molecules emit radiation at specific frequencies when their atoms change energy states. By detecting these faint signals, scientists can measure temperature, density, and motion, even in the deepest parts of molecular clouds. The data reveal a surprising picture. The gas isn't completely motionless. It has slow internal currents, subtle flows guided by gravity and magnetic fields. The long sleep is not perfect stillness, it's the quiet before structure takes shape. There's a curious symmetry in this part of the galaxy's story. the same atoms that lie dormant here once burned inside stars. They were part of violent fusion reactions, flung outward in explosions heated to millions of degrees. Now, after billions of years, they find themselves cooled to near zero, moving softly through the dark. It's a reminder that every element experiences the full range of existence, from chaos to calm, from fire to silence. The galaxy, for all its motion, spends most of its time in this slow state, atoms resting between acts of creation. The long sleep of atoms also defines how the galaxy looks from afar. The coldest regions emit little light, appearing as dark voids against the brighter background of stars and nebulae. But those voids are not empty. They are dense with potential, the future homes of stars and planets. In a way, they're the galaxy's memory, places where old matter waits to become new again. The light that doesn't reach us from these regions isn't lost. It's simply trapped, waiting for something to wake it. Temperature in space is an abstract concept. On Earth, we associate it with sensation, warmth, coldness, comfort, pain. In interstellar space, temperature is about motion. The slower the atoms move, the colder the gas. When motion nearly stops, when energy levels flatten out, we reach the conditions found in these vast dark clouds. It's a realm where chemistry operates at the edge of possibility. Reactions take years to complete, sometimes longer, but they still occur. Given enough time, even in the coldest void, complexity arises. Some of the most interesting discoveries about the long sleep of atoms come from spectroscopy, the study of light's interaction with matter. When light from a distant star passes through a cold cloud, certain wavelengths are absorbed by the atoms and molecules within it. These absorption lines tell us what's present and how much. By studying them, astronomers can measure the abundance of elements and trace how matter moves through the galaxy. They can even detect the tiny temperature differences between regions, revealing where gas is warming or cooling. Each line in the spectrum is a whisper from sleeping atoms, a record of their presence in the dark. Though the phrase cold often suggests lifelessness, these regions are anything but dead. They're chemical laboratories where some of the most essential molecules for life form, organic compounds, including amino acids and simple sugars, have been detected in cold interstellar clouds. They form slowly, through reactions on the surfaces of dust grains and within icy mantles. When stars eventually heat these regions, the compounds evaporate and mix into new planetary systems. The ingredients of biology are born during the long sleep, in the quiet that precedes light. This process connects the smallest scales to the largest. The same atoms that rest between stars also rest within us. The oxygen in your lungs, the carbon in your cells, the nitrogen in your DNA, all were once part of the long sleep. They drifted through cold interstellar space before finding their way into clouds that form the sun and the earth. When you breathe, you're moving atoms that spent billions of years waiting in silence. The boundary between human life and cosmic stillness is only time. Even the structure of galaxies depends on these quiet atoms. Their slow movement allows the interstellar medium to maintain its balance. Gravity pulls, but magnetism and thermal pressure push back. The result is a system that evolves without collapsing too quickly. The stillness acts as a kind of control, regulating the pace of star formation. Too much turbulence and clouds would disperse before stars could form. Too little, and everything would collapse at once. The long sleep of atoms is in this sense a form of galactic moderation. It keeps the rhythm steady. When we think about movement in space, we often imagine speed. Light racing through the void, stars orbiting the galactic center, planets revolving around suns. But most of the universe exists in the opposite state. Motion is rare, and change happens so slowly that it might as well be stillness. From a cosmic perspective, the periods of rest outweigh the bursts of activity by orders of magnitude. The long sleep is not an exception, it's the rule. Every bright moment of creation is surrounded by epochs of quiet preparation. Even in these cold, slow regions, energy never completely stops. The universe doesn't allow true stillness. Quantum mechanics tells us that even at absolute zero, atoms retain a faint vibration known as zero-point energy. It's a reminder that the long sleep is not death. It's a state of minimum motion, not total absence. The atoms wait, vibrating softly, maintaining the faint hum that keeps the cosmos alive. If there is such a thing as the sound of the universe resting, this would be it. The long sleep of atoms also reminds us that time itself behaves differently on such scales. To an atom drifting between stars, there's no awareness of slowness or patience. Time doesn't pass in the way we perceive it. It's only from our perspective, bound to the rhythm of days and years, that this stillness seems endless. For the galaxy, millions of years are as natural as a breath. The atoms resting in the dark are part of that rhythm, a pause between inhalations, waiting for gravity or radiation to call them back into motion. When a nearby supernova eventually sends shockwaves through these regions, the atoms will stir. The energy will ionize the gas, heat it and set it moving again. The long sleep will end and the cycle will begin anew. Some of the atoms will join in forming new stars. Others will become part of planets or comets. A few will remain in interstellar space, cooling once more after the disturbance passes. In time, they'll return to rest, beginning another long sleep. The calm between stars, the slow drifting of atoms, is what gives the galaxy continuity. It connects one generation of stars to the next. It carries the chemical memory of everything that has ever burned or frozen. It ensures that even in the darkest places, the ingredients of creation remain ready. The long sleep of atoms is not a void, it's a foundation. It's the quiet from which motion emerges, the stillness that allows light to return. And so, out there, between solar systems, billions upon billions of atoms rest, scattered through the galactic night. They move too slowly to collide, too gently to glow, too quietly to announce themselves. But in their patience lies everything that will ever be made. One day, gravity will call to them again, and they'll gather, warm, and shine. Until then, they drift in silence, unhurried, suspended in the long sleep that fills the space between stars. Out in the spaces between solar systems, where the gas thins to almost nothing and the dark seems unbroken, there are storms that never flash and never roar. They have no sound, no clouds, no rain, but they carry more energy than any weather we know. These are storms of particles, not air or water. Protons, electrons, and atomic nuclei, stripped and accelerated to near the speed of light, racing endlessly through the galaxy. We call them cosmic rays. They travel silently through the interstellar medium, crossing light years of space, threading between magnetic fields, touching everything but seen by almost nothing. They are the quiet storms that fill the dark. Cosmic rays come from many sources. Some are born in the violent shock waves of supernovae, where massive stars end their lives in explosions so powerful that they can outshine entire galaxies. Others come from neutron stars, pulsars, or the swirling disks of matter around black holes. There are even some that may originate beyond our galaxy, accelerated by immense structures in the wider universe, the vast filaments and clusters that connect galaxies together. Wherever they begin, once they're loose, they travel far. The Milky Way is filled with them, a continuous rain of invisible energy passing through everything, including us. If you could see these particles, the night sky would look nothing like it does now. Instead of a field of quiet stars, you'd see a faint, restless shimmer. Everywhere, particles racing, scattering, and spiraling around magnetic lines, each carrying the memory of some distant explosion. They move too fast to see directly, and their paths are twisted and curved by magnetic fields, so tracing one back to its origin is nearly impossible. Each one's journey is a random walk through the galaxy, a slow diffusion that can take millions of years. When a supernova explodes, its shockwave expands into space at thousands of kilometers per second. The front of that wave sweeps up the surrounding gas, compressing and heating it. Within that turbulent boundary, magnetic fields intensify, creating a natural accelerator. Charged particles caught in this environment bounce back and forth across the shock, gaining energy with each crossing. Eventually they're thrown free at speeds approaching light. In that moment, a cosmic ray is born. It will travel through the interstellar medium for eons, colliding occasionally with atoms, producing faint flashes of gamma rays or secondary particles, but mostly drifting unseen. Even though they are tiny and invisible, cosmic rays play an important role in shaping the galaxy. When they strike interstellar gas, they ionize it, breaking apart atoms and molecules. This changes the chemistry of the regions they pass through, influencing how clouds evolve and how new stars form. They can also heat the coldest parts of space, providing a trickle of energy where starlight never reaches. In dense molecular clouds, where temperatures hover near absolute zero, cosmic rays are often the only source of ionization, keeping a small but vital current of activity alive. Closer to home, the sun creates its own version of these silent storms. Solar flares and coronal mass ejections hurl charged particles into space, forming what we call solar cosmic rays. Most of them are confined within the solar system, but some escape into the galaxy. These smaller storms affect planets directly. When they reach Earth, our magnetic field deflects them, creating auroras as they collide with the upper atmosphere. The light that dances near the poles, green, red, and violet, is the visible trace of invisible particles colliding with atoms of oxygen and nitrogen. It's the quiet cosmic weather made visible for a few moments before fading back into stillness. The galaxy's magnetic fields guide cosmic rays, bending their paths into long tangled routes. They don't move in straight lines, but spiral along magnetic threads, scattering and diffusing as they go. This motion is slow and random, almost like smoke drifting in a room with unseen currents. It can take 1,000,000 years for a cosmic ray to cross the galaxy. During that time, it may pass through many regions: dense clouds, open space, magnetic bubbles, before escaping into intergalactic space. The Milky Way, in this sense, acts as a kind of container, a magnetic labyrinth where these silent storms wander endlessly. Despite their energy, cosmic rays are few. In a cubic meter of space, you might find a handful of them at any given time. But each carries immense energy, sometimes equivalent to that of a fast-moving baseball compressed into a single atom. The most energetic cosmic rays ever detected have energies millions of times greater than what we can produce in particle accelerators on Earth. No one knows exactly what creates them. Some may come from the most extreme events in the universe: colliding galaxies, active black holes, or the explosive birth of massive stars. Whatever their origins, they are the universe's messengers, crossing unimaginable distances to reach us. When these high-energy particles strike the upper atmosphere of Earth, they collide with molecules of nitrogen and oxygen, creating showers of secondary particles that cascade downward. Sensitive detectors, buried deep underground or spread across wide fields, capture these showers to study their properties. Every detection is a glimpse into something that began far beyond our reach. It's strange to think that, at this very moment, cosmic rays are passing through your body, through the walls, through the planet itself, barely interacting, continuing their journey. They are the most persistent travellers in the cosmos, and their paths run through everything. In the emptiness between solar systems, where light fades and matter thins, cosmic rays provide one of the few forms of motion. They are energy in its purest wandering state, carrying information about places we cannot see. Some are deflected by the magnetic boundaries of stellar winds. The sun's heliosphere, for example, acts as a shield, blocking many of the lower energy cosmic rays from entering the inner solar system. But beyond that shield, in the interstellar medium, the full flux continues unhindered, a quiet drizzle of particles from every direction. The Voyager spacecraft travelling beyond the heliosphere have measured this radiation directly. What they've found confirms what we long suspected, that even the deepest void between stars is filled with invisible activity. The effects of cosmic rays aren't limited to chemistry or temperature. They also influence the behaviour of magnetic fields themselves. As these particles move, they generate electric currents that in turn can strengthen or distort the surrounding magnetic structure. This feedback creates turbulence, a slow rolling motion that stirs the interstellar medium. Over time, it helps distribute energy evenly across vast regions. The balance between gas, dust, magnetic fields, and cosmic rays maintains the galaxy's stability. Without these silent storms, the Milky Way might look entirely different. Its arms less defined, its clouds less dynamic, its rhythm less alive. Astronomers study cosmic rays indirectly, because direct observation is nearly impossible. Telescopes can't see the particles themselves, but they can detect the light they create when they collide with matter or magnetic fields. Gamma-ray observatories reveal glowing halos around supernova remnants, the birthplaces of many cosmic rays. Radio telescopes detect synchrotron radiation, the faint radio waves emitted when charged particles spiral around magnetic lines. Together, these observations build a picture of the galaxy not as a static structure, but as a living system full of invisible motion. The storms of the interstellar medium aren't like the weather we know, but they follow similar rules. There are waves, currents, and turbulence, though everything happens on scales far larger and slower than anything on Earth. A supernova may create a ripple that travels for thousands of years, gradually spreading its influence across the galactic disk. Magnetic eddies swirl through space, twisting and stretching the field lines that guide particles. The energy flows continuously, never stopping, never quite repeating itself. Even in silence, the galaxy is always in motion. For all their energy, cosmic rays are fragile in another sense. Every collision, every deflection, every interaction saps a little of their strength. Over millions of years, they lose energy, their speed slowing until they blend into the general background of interstellar plasma. In that state, they join the long sleep of atoms once more, their storm spent. The cycle continues. Explosions create new cosmic rays, magnetic fields guide them, collisions slow them, and stillness absorbs them. Nothing is wasted. Energy becomes motion, motion becomes heat, and heat becomes quiet again. If we could stand outside the galaxy and watch it in light invisible to our eyes, we'd see it glowing softly with the traces of these silent storms. High-energy radiation would ripple through its arms, outlining the regions where supernovae have stirred the gas. Clouds would shimmer faintly where cosmic rays are dense, and filaments of magnetism would weave through it all. From that distant view, the Milky Way would appear alive, not in the biological sense, but as a system of constant renewal. Every storm leaves behind the potential for new creation. There's something quietly reassuring about the way energy circulates through the galaxy. Even the most violent events like the death of a massive star don't end in destruction. They feed the system, scattering particles that heat, shape, and seed the interstellar medium. The energy doesn't vanish. It changes form, becoming the soft background motion that fills the spaces between solar systems. The storms pass, the atoms rest, and somewhere else, another burst begins. For planets and living things, cosmic rays are both a danger and a gift. On Earth, most are deflected by our magnetic field and atmosphere, but a few make it through, leaving faint traces in rocks and even in our DNA. Over millions of years, this constant radiation has contributed to mutation and change, a subtle influence on the evolution of life. Beyond Earth, in the open interstellar medium, cosmic rays play a similar role for matter itself. They alter molecules, rearrange atoms, and occasionally trigger reactions that would otherwise never occur. Creation, it seems, often depends on a touch of chaos. Between solar systems, there are no boundaries, no walls to stop these particles. They move from one region to the next, carrying energy across the galaxy. Each one, in its long and winding path, helps connect distant places that will never meet otherwise. In this way, the cosmic rays act as the galaxy's messengers, travelling across billions of kilometres, passing through the darkness that holds everything apart. They remind us that even in the coldest, emptiest spaces, motion continues, faint but constant, quiet but vital. And so, through the silent storms of the interstellar medium, the Milky Way breathes, dust gathers, gas cools, atoms sleep, and energy moves between them, binding the whole into one continuous system. The cosmic rays are the unseen heartbeat of this process, a circulation of power too vast and too subtle to witness directly. Every supernova adds to it, every explosion feeds it, and every quiet moment in space carries its residue, a faint hum that runs through the galaxy's bones. It's easy to think of space as motionless, as a vacuum beyond weather or wind, but the truth is that it's full of invisible tempests, waves of particles, ripples of magnetism, flashes of high-energy light. The storms may be silent, but they shape everything, stirring the dust that forms planets, igniting the gas that births stars, and carrying the energy that keeps the galaxy in balance. Even here, in the stillness between solar systems, the quiet never means nothing is happening. It means everything is happening slowly, gently, endlessly. The cosmic rays will keep moving long after the stars that created them have faded. Their energy will spread through space, warming the cold, ionizing the dark, whispering across the distances until they too rest. And somewhere in that stillness, new storms will rise again. The galaxy's quiet weather never stops. It only pauses long enough for us to call it silence. If you could see the Milky Way without its stars, without the bright clusters or shining nebulae, you would still see a shape, faint, vast, and full of motion. It would look like something carved by invisible hands, a structure of filaments, bubbles, and arcs stretching across light years of space. But there are no hands, no tools, no visible sculptors at work. The forms of the interstellar medium, its clouds, its cavities, its waves of gas and dust, are shaped by forces we can barely imagine, acting so slowly that we only notice their results. They are the invisible sculptors of the galaxy, the quiet architects that shape everything between solar systems. The work begins with energy. When a star is born, it doesn't emerge gently. Radiation, stellar winds, and magnetic fields burst outward, pushing against the gas and dust around it. Even a single young star can blow a small cavity in its surroundings, a bubble where the gas has been cleared. Multiply that by thousands of stars forming across the spiral arms, and the galaxy becomes a landscape of overlapping shells and waves. Over time, these small cavities merge, forming vast structures, some hundreds of light years wide, carved entirely by starlight and motion. The most dramatic sculptors are supernovae. When massive stars die, their explosions send shockwaves racing through space, compressing and heating everything they touch. These shockwaves sweep up interstellar gas into expanding shells. The outer edges of those shells cool and condense, forming dense layers where new stars may one day form. The space inside the shell becomes a hot, low-density bubble. Over millions of years, these bubbles overlap, merging into enormous regions of turbulent gas known as superbubbles. The Sun itself drifts within one such region, a cavity created by generations of supernovae long before our solar system existed. It's strange to imagine that the space we travel through, the calm darkness that seems so still, is actually the aftermath of ancient explosions. The invisible sculptors worked long before we arrived, and their shapes, still define the paths of dust and gas today. Even in the emptiness between solar systems, the density of material is not uniform. There are ridges, filaments, and voids, the result of waves that have passed through over billions of years. Gravity alone could not create such complexity. The energy released by stars, their radiation, winds, and deaths, is what gives structure to the interstellar medium. The sculpting process doesn't stop when a supernova fades. The shock waves continue to ripple outward, meeting others, overlapping, and forming intricate patterns of compression and rarefaction. Each encounter leaves behind turbulence, a kind of cosmic weather that stirs the gas and dust. This turbulence drives motion on every scale, from small eddies a few light-years across to vast flows that span entire arms of the Milky Way. The interstellar medium, though thin and diffuse, behaves like a fluid in constant motion. It's shaped by invisible pressures, always shifting but never losing its form. Light, too, is a sculptor. Ultraviolet radiation from massive stars ionizes the gas around them, turning neutral hydrogen into glowing plasma. This process creates bright regions called H2 regions, where electrons and protons recombine to emit light. The edges of these regions form delicate boundaries, sharp, luminous fronts where radiation meets darkness. Over time, those fronts move outward, eating away at surrounding clouds, shaping them into pillars, arcs, and globes. The famous Pillars of Creation in the Eagle Nebula are an example of this work. Columns of dense gas left behind as radiation slowly erodes everything else. Everywhere in the galaxy, these interactions between light and matter carve patterns that seem intentional but are purely the result of physics. Where gas is dense, light pushes it aside. Where it's thin, radiation passes freely, leaving shadows that harden into structure. The result is a cosmic interplay between illumination and darkness, creation and erosion, repeated endlessly across space. Magnetic fields add another layer to the sculpture. They guide the flow of gas, shaping it into filaments that align with invisible lines of force. In some regions, magnetic tension resists compression, holding clouds in place. In others, it channels energy along narrow paths, focusing motion into streams. Observations from polarimetric telescopes show that many interstellar filaments follow the orientation of magnetic fields. Even in the absence of gravity or pressure, magnetism alone can create order, threading the galaxy with unseen geometry. The invisible sculptors also work through time, using patience instead of speed. A shock wave that takes thousands of years to cross a cloud might seem instantaneous on a cosmic scale, but for the gas it passes through, it's an eternity. Molecules are torn apart and reformed, dust grains shattered and rebuilt, atoms ionized and recombined. Each event changes the balance of forces, adjusting how the gas flows. Over millions of years, the repeated passage of such waves turns random distributions into coherent forms. Long filaments, shell-like cavities, and dense knots where stars will one day ignite. Astronomers studying these structures often describe them as remnants of motion, the frozen aftermath of energy that has long since dissipated. In a sense, the galaxy is a sculpture made of echoes. Every line and curve marks where energy once moved, where heat once pressed outward, where gravity once pulled inward. The shapes persist long after the events that formed them have ended. The bubbles carved by supernovae, for example, can last for tens of millions of years. Long after the stars that created them are gone, the marks remain, slowly fading as new forces take their place. In regions where multiple supernovae occur in close proximity, the sculpting becomes even more dramatic. The overlapping shock waves create enormous cavities, hundreds of light-years across, filled with hot, low-density gas. These cavities, known as superbubbles, often expand until they break through the galactic disk, venting gas into the halo above and below the plane. This outflow helps regulate the galaxy's balance, returning material to space that will eventually cool and fall back in. The process is sometimes called galactic recycling, but it's also a form of continuous carving. The galaxy reshapes itself from within, constantly reworking its own structure. Even the smallest events contribute. When a single star emits a steady stream of stellar wind, that wind collides with the surrounding gas, forming a bow shock. This shape, a curved wave that wraps around the star, marks the point where the outward flow meets resistance. Similar structures can be found around entire clusters of stars, where their combined winds create vast cavities. From afar, these look like bubbles within bubbles, an intricate pattern of layers built over eons. If you could see the galaxy in motion, sped up 1 billion times, you'd witness a dance of endless transformation. Clouds would form and dissolve, filaments would stretch and twist, bubbles would expand and merge. The invisible sculptors never rest. Their tools are light, gravity, magnetism, and time. Their work is both creative and destructive, erasing one pattern to make another. Yet despite the chaos, the overall structure remains coherent. Spiral arms, central bulge, outer halo, all maintained by the combined effect of these forces working in balance. The interstellar medium, for all its thinness, responds sensitively to even small disturbances. A shock wave passing through can trigger star formation in one region and suppress it in another. Radiation can erode one cloud while compressing its neighbour. Magnetic fields can funnel gas into long threads, forming future star nurseries. Each of these processes interacts with the others, producing complexity that no single cause could explain. The galaxy's architecture isn't designed, it's emergent. The invisible sculptors work independently, yet together they create harmony. Even our solar system bears the marks of their influence. The cloud that gave birth to the sun and planets likely formed at the edge of a superbubble, where the shock wave from an older supernova compressed gas into a dense region. The isotopes found in meteorites suggest that nearby massive stars enriched the material with heavy elements before the sun formed. In a literal sense, our origins were sculpted by the deaths of other stars. The space between solar systems carries that legacy, a silent record of shaping forces that extend far beyond what we can see. The scale of this sculpting defies human comparison. On Earth, wind carves rocks over centuries, rivers cut valleys over millennia, glaciers reshape continents over ages. In the galaxy, the same happens with gas and dust, but on timescales so vast that they seem infinite. A single bubble of ionized gas may take 1 million years to expand. A filament may persist for tens of millions before dispersing. Every curve, every gap, every density gradient in the interstellar medium is a record of time made visible, the trace of invisible hands that never stop working. The invisible sculptors are not perfect artists. Their creations are temporary, transient arrangements in a system that never stops evolving. But that impermanence is part of what keeps the galaxy alive. Without constant motion, without the ongoing push and pull of energy and matter, everything would settle into equilibrium, a state without form or light. The turbulence, the shocks, the flows, these are what prevent stagnation. The galaxy's beauty lies in its unfinished state, in the way it is always being made and remade. In a sense, the interstellar medium is like a slow conversation between forces. Radiation pushes, gravity pulls, magnetism guides, and pressure resists. The results of that dialogue are the structures we see: clouds shaped like fingers, shells wrapped around voids, filaments connecting distant regions. Every motion leaves an impression, and every impression guides the next. The invisible sculptors don't plan their work, they simply respond to one another, creating patterns that never repeated. Astronomers can now simulate these processes with computers, using equations to model how gas and dust move under the influence of these forces. The results are strikingly similar to what we observe in real galaxies. Turbulence creates filaments, radiation carves cavities, Gravity gathers knots that ignite into stars. Even in simulation, the patterns emerge naturally, as if the laws of physics themselves were the artist's hand. The beauty of the galaxy doesn't come from intention. It comes from inevitability, from the way energy and matter, given enough time, shape themselves into structure. Out there, between the solar systems, every atom carries the mark of these processes. Some drift through the aftermath of an ancient explosion. Others move along the edge of a shock wave. Others rest in the calm between disturbances. The space may appear empty, but its form is sculpted by history. The invisible forces that move through it are still working, still carving, still shaping the next generation of stars and worlds. And as we look out into the darkness, trying to understand what lies between, we're really looking at the results of countless unseen actions, the quiet work of energy moulding the fabric of space itself. The galaxy is not static, and the emptiness between stars is not unformed. It's full of memory, full of structure, full of invisible sculptors that never tire. They've been at work for billions of years, and they'll continue long after our own system has faded into the same dark medium. The beauty of their work is that it never ends. Every bubble will eventually collapse, every filament will disperse, every shock wave will fade into stillness, and then, slowly, new ones will form. The cycle continues, reshaping the galaxy without pause, guided by forces we can't see but can trace through their effects. Between the solar systems, where darkness reigns and silence seems absolute, the sculptors are always moving, shaping the invisible architecture that gives the Milky Way its form, quietly ensuring that even the emptier spaces are full of meaning. If you could pull back far enough to see the Milky Way from the outside, you'd notice that its light doesn't spread evenly. It gathers in arms and lanes, clusters and filaments stitched together like a living network. The spiral arms themselves are only the brightest threads, the ones lit by countless stars, but between them lies an even greater structure, a web of gas, dust, magnetism, and energy that connects everything. This web isn't visible to ordinary sight. It reveals itself only through radio waves, infrared light and X-rays, yet it holds the true shape of the galaxy, the underlying framework that binds the stars together. This web is the interstellar medium seen as a whole. The gas, dust, magnetic fields and radiation we've followed so far are not isolated. They weave into a single connected system that stretches across the galactic disk and out into its halo. It's the hidden skeleton of the Milky Way, an intricate mesh of filaments and voids that defines how stars form, how energy flows, and how matter circulates. Even though the galaxy appears calm when viewed from Earth, on the scale of thousands of light years, this web is in constant motion. If you could somehow travel through it, you wouldn't see boundaries between regions. Instead, you'd drift through a continuous texture of varying density and temperature. One moment you'd be inside a cold molecular cloud, dense and dark, where dust blocks all starlight. The next you'd pass into a warm, ionized region glowing faintly in hydrogen's red light. Beyond that you'd find vast cavities of hot gas, the remnants of long vanished explosions. Each layer blends into the next, connected by filaments of material that stretch for hundreds of light years. There's no true emptiness, only thinner and thicker strands of the same network. This web within the Milky Way behaves in ways both familiar and alien. It resembles the structure of a living tissue, with filaments acting like arteries, carrying gas and energy through the disk. It also echoes the large-scale structure of the universe itself, where galaxies form along cosmic filaments separated by immense voids. The same physical laws shape both scales: gravity, turbulence, pressure, and magnetism. The galaxy mirrors the universe that contains it, repeating its geometry in miniature. Astronomers have mapped parts of this interstellar web using many different methods. Radio telescopes trace the faint emission from neutral hydrogen. revealing long, sinuous structures that thread through the spiral arms. Infrared observations show where dust collects along those filaments, marking the paths where stars are forming. X-ray satellites detect the hot plasma filling the spaces between, heated by ancient supernovae. When these different views are combined, the galaxy emerges not as a flat disk, but as a textured, three-dimensional maze, a system of layers and channels, each with its own temperature and rhythm. In some regions, the filaments are strikingly organized. The Taurus molecular cloud, for example, shows hundreds of thin threads of gas and dust, many running parallel, all following the direction of the local magnetic field. These filaments act as birthplaces for stars. Along their lengths, gravity gathers material into denser knots, which eventually collapse into protostars. The filaments feed those newborn suns like veins supplying nutrients, channeling gas from the wider cloud into the core. Once the stars ignite, their radiation begins to erode the very filaments that created them. It's a self-limiting process, one that repeats across the galaxy. Elsewhere, the web is more chaotic. Supernova remnants overlap, magnetic fields twist, and turbulence creates curls and waves in the gas. These tangled regions may look disordered, but they still follow patterns of flow and feedback. Energy moves through them like ripples on a pond, stirring the gas, mixing elements, and preventing stagnation. The turbulence spreads metals from one region to another, enriching the galaxy and ensuring that new generations of stars inherit the ingredients for planets and life. Even apparent chaos has purpose here. It's the mixing mechanism that keeps the galaxy evolving. One of the most fascinating aspects of the interstellar web is its scale. The filaments within molecular clouds can be a few light years long. Larger ones, like the giant structures known as spurs or bridges, can extend for hundreds. Some connect to spiral arms, forming vast corridors of gas that guide matter through the disk. Above and below the galactic plane, plumes of hot gas rise into the halo, connecting the dense interior to the thin outer regions. These outflows and inflows act as the galaxy's circulation, carrying material outward and drawing fresh gas back in. The Milky Way doesn't exist in isolation. It exchanges matter with the surrounding intergalactic medium through these channels. The solar system moves through this web just like everything else. As the Sun orbits the galactic center, it drifts in and out of different regions, from the relatively empty interior of the local bubble to denser clouds beyond. Each change affects the boundary of the heliosphere, the bubble of plasma created by the solar wind. The shape and size of that boundary fluctuate with the surrounding conditions, meaning that our planetary system is constantly responding to the web around it. We're not separate from the interstellar medium, we're swimming in it, part of its flow. This galactic web also carries the imprint of the Milky Way's history. The spiral arms are not fixed structures but patterns of density waves, regions where gas and stars bunch up as they orbit the center. As material moves through an arm, it's compressed, forming new stars. Those stars then drift onward, leaving the denser region behind. Over time, this motion creates the illusion of a permanent spiral, even though the actual matter is always changing. It's a wave pattern in a fluid, the same principle that shapes the ripples on water or the motion of sound. The interstellar web provides the medium through which those waves travel. Gravity is the web's main architect, but it doesn't work alone. Magnetism, turbulence, and radiation all add their own layers of influence. Gravity pulls material together, while turbulence resists collapse, breaking large structures into smaller fragments. Magnetic fields guide the flow of charged particles, while radiation from massive stars heats and pushes against the gas. The result is a balance between contraction and expansion, between order and motion. The web exists in that balance, never stable, never collapsing, always changing shape but maintaining coherence. If you could follow the movement of matter through this web, you'd see a slow but continuous cycle. gas flows along filaments toward dense clouds where stars are forming. When those stars ignite, their energy drives winds that push gas back out, filling nearby cavities. Supernovae blast holes in the disk, sending material into the halo. There it cools, falls back down, and re-enters the filaments. Every atom in the galaxy participates in this loop at some point, travelling from void to cloud, from star to space, from hot to cold. The interstellar web is not a static structure. It's the circulatory system of a living galaxy. At its heart, the web reflects the principle of interconnectedness. No region of the Milky Way exists in isolation. The shockwave from a dying star in one spiral arm can eventually influence the formation of stars in another, carried by the magnetic and gaseous links between them. Even the faintest regions of diffuse gas are part of a continuous chain of cause and effect. Energy flows, matter moves, and the galaxy adapts. It's a system defined by feedback. Every action has a response somewhere else, even if it takes millions of years to appear. The web also helps maintain the Milky Way's stability. Without it, the galaxy's rotation would tear its disk apart. The gravitational pull of the arms, the pressure of the gas, and the resistance of the magnetic fields work together to keep everything in balance. The dense filaments and molecular clouds act as anchors, while the hot gas and magnetic fields distribute pressure evenly. Over cosmic time, this equilibrium allows the galaxy to retain its spiral structure instead of collapsing into chaos. For astronomers, mapping the galactic web is like tracing the nervous system of a creature too vast to comprehend. Every wavelength of light offers a different clue. Radio observations show the neutral hydrogen backbone. Infrared reveals the dust lanes. X-rays expose the hot gas that fills the gaps. Even cosmic rays leave their marks, tracing paths through magnetic channels. By combining all these views, scientists can reconstruct a picture of the galaxy that goes beyond stars, a map of the invisible framework that underlies everything. Recent observations have even revealed enormous vertical structures extending above and below the galactic plane, giant bubbles of energetic gas and radiation, likely produced by past outbursts near the Milky Way's centre. These Fermi bubbles, named after the telescope that discovered them, rise tens of thousands of light-years into space. They show that the web extends not just across the disk, but far into the surrounding halo. The galaxy's structure doesn't end where the starlight fades. It continues outward, fading gradually into the intergalactic medium. In a broader sense, the web within the Milky Way mirrors the networks we see at every level of nature. The veins of a leaf, the flow of rivers, the filaments of neurons, the cosmic web of galaxies, all share the same underlying mathematics. Turbulence, branching, feedback, and flow create patterns that repeat across scales. The interstellar web is the galaxy's version of this universal geometry. It connects microphysics, atoms and molecules, with astrophysics from stars and galaxies. It shows that even in the larger systems, structure arises naturally from simple interactions. From our small vantage point inside one arm of the galaxy, it's hard to sense this unity. The stars we see appear scattered randomly, their arrangement without clear order. But when we step back, when radio maps and infrared surveys reveal the full picture, we see that the randomness is only apparent. Every cloud, every filament, every region of space fits into the wider pattern. We're inside one thread of the Milky Way's vast web, surrounded by others, moving with them through the slow rotation of the disk. The web isn't static, and it isn't eternal. Over billions of years, it will shift as the Milky Way merges with nearby galaxies, as new stars form and old ones die. The filaments will stretch, the arms will warp, and the overall shape will evolve, but the principle will remain, that everything connects, that every piece of matter belongs to the same network. Between the solar systems, the web continues to hum quietly, carrying the motion of atoms, the heat of stars, and the memory of time itself. If the Milky Way could be heard instead of seen, the sound would not be a note or a tone. It would be a constant low resonance, the collective vibration of all these flows and connections spreading through the interstellar medium. It would be the sound of the galaxy's web in motion, rising and falling over millions of years, a hum that never fades entirely. The silence we perceive is simply the limit of our senses. Beyond that limit, the web continues to move, to bind, to shape, and as we orbit within it, unaware of the scale of what surrounds us, we are part of that web too. Every atom in our bodies was once carried through its filaments, shaped by its flows, and returned to form something new. The same web that connects stars connects us. The Milky Way's great structure isn't out there in the distance. It runs through us, through every breath, through every atom that was once dust, gas, and light. The galaxy is not a collection of isolated systems. It's one connected body, and we are suspended within its invisible strands, moving quietly through its endless, intricate design. When a photon is born, it does not know where it will end up. It has no destination, no sense of travel, no awareness of time. It is simply released, a packet of energy, a quantum of light, set free into the vastness of space. The moment it leaves its source, it becomes part of the quiet traffic of radiation that fills the Milky Way, joining an uncountable number of others that are constantly crossing the dark. Every photon carries with it a story, where it came from, what it passed through, and how it changed along the way. Its journey is the most common, most continuous process in the galaxy, yet it happens in silence. The journey begins deep inside a star. In the dense, hot core, where nuclear fusion converts hydrogen into helium, photons are born in staggering numbers. Every second, the sun alone produces around 1045 photons, but none of them escape quickly. The core is so dense that each photon is immediately absorbed by another particle, scattered, re-emitted, absorbed again, and re-emitted again. It can take thousands, sometimes even hundreds of thousands of years, for a single photon to travel from the core of a star to its surface. In that time, it has been absorbed and recreated so many times that its original identity is long lost. What finally leaves the surface is the result of an endless relay, a light that has been passed from one particle to another until it finally reaches freedom. Once that photon escapes into space, its environment changes completely. No longer trapped by density, it moves freely through the vacuum. In the near emptiness between solar systems, it travels straight unless something gets in its way. In a single second, it can cover almost 300,000 kilometers. In a year, it crosses nearly 10 trillion kilometers, 1 light year. Its motion is so fast and smooth that time, from its own perspective, ceases to exist. From emission to absorption, for a photon, there is no in-between. It simply begins and ends, while to us the journey may last millennia. As it travels through the interstellar medium, the photon encounters dust, gas, and magnetic fields. Each of these can alter its path or its energy. A dust grain might scatter it, changing its direction but not its speed. A gas cloud might absorb it, causing the photon's energy to heat the atoms within. Some of that energy is later re-emitted as infrared light, a new photon born from the ashes of the old. In this way, light continually transforms, passing its energy forward in a chain that stretches across the galaxy. The photon that leaves one star may, in a sense, live on as the warmth of another cloud or the faint glow of another region. Not all photons are the same. Some are high-energy gamma rays, born in violent events like supernovae or near black holes, carrying enough energy to strip electrons from atoms. Others are lower-energy infrared photons, produced by dust grains warmed by starlight. Between them lies the full spectrum: ultraviolet, visible, and radio. Each type travels differently, interacting more or less with the medium it passes through. High-energy photons cut through gas easily, but are eventually absorbed by dense regions. Low-energy photons are scattered and diffused but can travel immense distances. Together, They create a complex web of radiation that fills every part of the Milky Way. For astronomers, photons are the only direct messengers from the cosmos. Every observation, every image, every spectrum is made of light that has travelled across space to reach us. When a telescope collects starlight, it's gathering photons that began their journey long before our species even existed. A single ray of light from a star 1,000 light years away began its journey when early humans were just discovering fire. The photons arriving in our eyes tonight carry messages written long before our world took shape. As a photon travels, its energy slowly changes. Space itself stretches under the influence of the galaxy's motion and gravity, and with it the wavelength of light. This process, known as redshift, doesn't just happen on cosmological scales. Even within the Milky Way, photons lose small amounts of energy as they climb out of gravitational wells or pass through expanding regions. What begins as a blue photon may arrive as red, its wavelength stretched just enough to shift its colour. These changes are subtle, but they contain valuable information about the structure and motion of the galaxy. By studying them, astronomers can map where matter lies and how it moves. Sometimes, a photon's journey is far from straight. Gravity bends its path. When it passes near a massive star or planet, the space around that object curves, and the photon follows the curve. This bending of light, called gravitational lensing, can focus or distort the image of a distant source. In extreme cases, one object can create multiple images of another, or even amplify its brightness. Though subtle within our galaxy, this effect is constant, shaping the way we perceive everything we see. No photon travels through perfectly flat space. Each one follows a slightly curved trajectory through the invisible contours of gravity. Even in the emptiest regions, the photon is never completely alone. It moves through a faint sea of other radiation, starlight from every direction, cosmic microwave background photons left over from the early universe, and the glow of dust warmed by the energy of past generations of stars. The space between solar systems is filled with this quiet radiation field, an ambient light that never stops flowing. Each photon passing through adds a tiny contribution, a ripple in a sea of endless motion. The journey of a photon doesn't end until it meets matter again. It might collide with a dust grain, be absorbed by an atom, or strike the surface of a planet. When it hits, its energy transforms once more into heat, into chemical reaction, into electrical current, or into the simple act of vision. When you look at the night sky, the photons striking your retina are ending their journeys. Each one has crossed unimaginable distances and times to reach that single moment of absorption. For the photon, the trip is instant. For us, it's the arrival of ancient history. Some photons never reach a destination. They travel endlessly, their wavelengths stretching with the expansion of space until they become too faint to detect. Others are absorbed and re-emitted countless times, their identities continually renewed. The galaxy, in this sense, is a vast recycling system of light. Energy flows from stars into space, through dust and gas and back again, transformed at every stage. The photons themselves are temporary carriers of this energy, short-lived couriers in an unending exchange. Inside dense clouds, where starlight cannot penetrate, photons are rare. But even there, radiation from cosmic rays and chemical reactions provides a faint glow. Molecules emit specific wavelengths as they rotate and vibrate, creating a soft radio signature. This light travels freely through the dark, providing astronomers with a way to study regions hidden from optical view. In a galaxy where most of the volume is filled with darkness, it's this faint emission that reveals the structure of the unseen. There's something quietly profound in the thought that every photon travels straight and steady, never slowing, never aging, yet telling us the story of time itself. The Milky Way's glow, the faint band we see arching across the night sky, is the combined light of billions of these travellers. Some come from nearby stars, their paths short and unbroken. Others come from distant clusters, passing through clouds, fields, and magnetic waves before reaching us. Together, they form a kind of history written in motion, a record of how light and matter interact across billions of years. For those photons that reach Earth, their last moments are humble. They enter the atmosphere, scattering among molecules of nitrogen and oxygen. Some are absorbed, warming the air. Others are bent and refracted, painting the sky blue in the day and red at sunset. A few survive the journey all the way to the ground, striking eyes, cameras, or sensors. Their existence ends as suddenly as it began, their energy absorbed and transformed once more. But in that final instant, they complete the connection between the cosmos and us. Even within our own solar system, the journey of photons continues to shape everything. Sunlight drives weather, photosynthesis, and the cycle of life. Reflected light defines how planets appear. The glow of the zodiacal dust is sunlight scattered by countless grains between planets. Each of those photons is both local and galactic, born in a star that formed from ancient clouds of hydrogen, part of a chain that stretches back to the beginning of the universe. When it touches Earth, it carries the memory of that lineage, the quiet continuity of light. Some photons travel inward rather than outward. In the dense environments around black holes, light can orbit, trapped temporarily by gravity before escaping or being swallowed. In those regions, photons reveal the most extreme distortions of space and time. The light we observe from matter swirling around black holes is the final signal before it disappears beyond the event horizon. Even here, at the edge of physical possibility, light serves as the only messenger. It is what lets us glimpse the unseeable. The galaxy's appearance, its colour, shape, and brightness, is entirely determined by the behaviour of photons. Without them, it would be invisible. Every bit of information we have about the universe comes from light in some form. We never touch the stars or the clouds directly. We interpret their light. Each photon, regardless of its source, contributes a piece of the puzzle, a single data point in a story too large to see all at once. As photons leave the Milky Way, escaping into intergalactic space, they become part of an even greater sea of light, the cosmic background that fills the universe. Most will never encounter another particle again. They'll travel endlessly, fading into the far reaches of space as the universe expands. Their journey will never truly end because there's no destination, only distance. The light that never arrives anywhere is still part of the great circulation of energy that defines existence itself. Every photon begins in one place and ends in another, but the path in between, the countless interactions, scatterings, and absorptions, is what connects everything. The stars that emit, the dust that absorbs, the planets that reflect, the eyes that see, all are nodes in the same continuous flow of light. The Milky Way is not just a collection of matter, it's a network of radiation in constant motion, each photon a carrier of the galaxy's memory. So when you look up at the sky and see that faint pale ribbon stretching across the dark, you're not just seeing distant suns, you're seeing the combined work of countless photons, each one a traveller that crossed immense distances and times to reach you. They began in the hearts of stars, moved through the thin breath of the interstellar medium, slipped between magnetic fields, scattered off dust, and finally arrived here. The light in your eyes is the final step in their long, silent voyage. And even as you see it, new photons are already beginning their own journeys, setting out across the galaxy, carrying the story forward through the endless night. Every civilization that has ever looked up at the sky has wondered whether something might be looking back. The thought comes easily in the stillness of night, that perhaps the silence isn't truly empty, that somewhere across the galaxy, another world might be sending out its own quiet signals just as we do. Between solar systems, between the countless stars of the Milky Way, there drifts not only light, dust, and gas, but the faint possibility of communication, messages carried by waves that cross the darkness. It's an idea both scientific and deeply human, that the void might hold not just matter, but meaning. The galaxy is already filled with messages, though not the kind we write. Radio waves from pulsars, bursts of X-rays from neutron stars, and the slow hum of cosmic background radiation all carry information about what the universe is doing. Every atom that absorbs and re-emits light is, in its own way, sending a signal, an announcement of its temperature, its velocity, its state. These natural transmissions fill every corner of space, overlapping, blending, forming a constant background of radiation. In that sense, the void is never silent. It's always speaking in the language of physics. We just learned to listen late. When humans first built radio telescopes capable of detecting faint signals from space, it didn't take long before the question arose, could some of those signals be deliberate? The first pulsar, discovered in 1967, was so regular in its rhythm that it was briefly nicknamed LGM-1, Little Green Men. The precision of its pulse, arriving every 1.33 seconds without fail, seemed almost too perfect to be natural. But it was natural, a rotating neutron star beaming radiation from its magnetic poles. Even so, that moment showed how instinctively we associate regularity with intention, how ready we are to interpret order as communication. Between solar systems, radio waves travel almost without hindrance. Dust can absorb visible light, but long wavelengths pass through easily. That's why, when we decided to send our first messages beyond Earth, we chose radio. It's the medium that the galaxy itself already uses. Since the middle of the 20th century, powerful radio telescopes have both listened for and transmitted signals across the cosmic sea. The faintest ones come from our own machines, navigation satellites, radar pings, and television broadcasts, leaking slowly into space. These signals spread outward as expanding spheres of radio noise, growing weaker with every light year. After a century of broadcasting, they've reached only a tiny portion of the Milky Way, a sphere about 100 light-years wide, still deep within our own spiral arm. Beyond that, our messages are too faint to distinguish from background static. The space between solar systems is vast enough that even light, moving at its relentless speed, takes thousands of years to cross from one side of the galaxy to the other. Any message we send today, if detected at all, would arrive long after the civilization that sent it has changed or vanished. In that way, communication between stars is less a conversation and more an act of preservation, a way of saying we were here, even if no one answers. It's a gesture toward continuity in a universe that offers none. In 1974, we sent one of the first deliberate interstellar messages from the Arecibo Observatory in Puerto Rico. It was a simple pattern of binary data, designed to be understood by logic rather than language. Numbers, atomic numbers, DNA structure, and a diagram of our solar system. The signal was aimed at a cluster of stars 25,000 light-years away. It was a brief transmission, only 3 minutes long, but even if it travels uninterrupted, it won't arrive at its destination for another 25 millennia. Whether anyone will be there to receive it, or whether our own species will still exist when it does, is unknown. Yet that's not the point. The act of sending it was itself an expression of curiosity, a way of placing a thought into the great silence. But not all messages are intentional. Every photon that leaves a planet, every pulse of light from a city, every reflection from a satellite is information leaking into space. The galaxy is full of unintentional broadcasts, the quiet electromagnetic footprints of civilizations, if any exist. For us, it's radio waves. For others, it might be something we can't yet detect. The interstellar medium doesn't preserve these signals forever. As they travel, they weaken, scattered by gas and absorbed by dust, until they fade into the background noise. The void remembers only briefly, but for a time, it carries our voice. The search for those voices, the search for extraterrestrial intelligence, or SETI, is one of the most patient scientific efforts ever undertaken. It doesn't rely on hope so much as on discipline, listening carefully, filtering out natural sources, analysing the data for patterns that could signify intention. Most of what we find are natural phenomena, pulsars, quasars, flaring stars, but the act of searching keeps us aware of how full of signals the universe already is. Even in their absence, the effort teaches us to listen more deeply, to refine our understanding of what the galaxy itself is saying. And the galaxy does speak. Pulsars send precise time signals that can be used as cosmic beacons, allowing navigation across interstellar distances. Quasars emit radio waves that can be detected billions of light-years away, marking the locations of the universe's most energetic regions. Supernova remnants glow in every wavelength, broadcasting the physics of their explosion. Even the neutral hydrogen that fills most of interstellar space emits a faint radio line at 21 centimeters, a natural signal that maps the structure of the Milky Way. Every frequency carries some kind of message, written not in words but in patterns of energy. When we listen for artificial messages, we're really listening for patterns that break those natural rhythms, narrowband signals that don't occur in nature, regular pulses or modulated sequences that suggest encoding. So far, none have proven real, but the effort continues. The void remains unbroken by confirmation, though not by imagination. The search itself is part of our story, an extension of the same curiosity that led us to look up in the first place. Even silence, sustained for decades, is a kind of response. It tells us how much we still have to learn about what it means to be alone in a galaxy of 100 billion stars. Communication across such distances requires more than technology. It requires a different kind of patience, one that accepts that a message might take longer to arrive than any single life, any single civilization. In that sense, sending a message into space is more like planting a seed in a forest you'll never visit. You do it not because you expect to see it grow, but because you want the forest to be more complete for your having been part of it. The void, for all its distance, invites that gesture. Between solar systems, radio waves travel outward forever, spreading thinner with distance. They're absorbed slowly by the interstellar medium, converted to heat, scattered, or redirected. Some may drift for millions of years before ever striking anything solid. A few may cross regions dense enough to distort them, their frequencies shifted by motion or magnetic fields. Most will fade into the cosmic background. But each wave, for as long as it exists, carries a pattern, the imprint of intention, of structure, of mind. And in the other direction, countless natural messages arrive at Earth every day. We are constantly bathed in the galaxy's radiation, the hum of hydrogen, the burst of flares, the whisper of distant quasars. Each photon and radio wave tells us something about the processes happening far away. The same medium that could, in theory, carry a deliberate message, already brings us a constant stream of natural ones. The galaxy doesn't need to speak in our language to tell us what it is. Even silence can be informative. The absence of detectable signals from other civilizations, known as the Fermi paradox, raises questions about how common life and intelligence might be. Perhaps communication is rare. Perhaps civilizations don't last long enough to overlap in time. Or perhaps their messages travel in ways we don't yet recognize, through neutrinos, gravitational waves, or technologies beyond our imagination. Whatever the reason, the quiet stretches across the galaxy like an unanswered question, one that deepens rather than diminishes our curiosity. In a way, we've already begun receiving messages from the void, though they weren't meant for us. The cosmic microwave background, the faint afterglow of the Big Bang, is the oldest message in existence. It's not a communication in any deliberate sense, but it carries information from the earliest moment when light could move freely through space. Every photon in that background has been travelling for more than 13 billion years, carrying with it a snapshot of the universe as it once was. When we detect that radiation, we're not just listening to space, we're listening to time. Our own attempts to send messages into the void are humble compared to that. We've launched plaques on spacecraft, records engraved with sounds and images of Earth, instructions on how to find us. The Voyager and Pioneer probes carry these messages, drifting now beyond the edge of the solar system, entering the interstellar medium. They'll keep travelling long after our planet has changed beyond recognition. Someday, if anyone or anything finds them, they'll be silent relics of a species that once wondered about the stars. Even if no one ever does, the gesture itself means something. It's an acknowledgement that communication is more than exchange. It's an offering. Between solar systems, messages, whether natural or intentional, share the same fate. They travel until they fade, absorbed by the medium that fills space. Some leave traces in the form of ionized gas or scattered radiation. Others simply vanish into heat. Yet the act of sending, the act of listening, ensures that the void is never truly mute. The galaxy hums with signals, a low and constant background that holds every story ever told by light and energy. Perhaps that is what communication in the universe truly is. Not a dialogue, but a chorus, uncoordinated and unending. Every star, every planet, every living thing contributes its own signal, intentional or not, and together they form the electromagnetic texture of the Milky Way. To listen is to participate in that shared existence, to recognize that silence is only what we hear when we focus on one frequency instead of all of them. The void isn't empty. It's saturated with messages, most of which we'll never decipher, but all of which make the galaxy what it is. The signals that drift between solar systems are fragile, but so are we. Yet we keep sending them, keep listening, keep trying to translate the patterns in the noise. Because somewhere, in the vast dark, the possibility of connection lingers, not as a promise, but as a principle, that everything that can emit will, that everything that emits will be received somewhere, sometime, even if that receiver is only the galaxy itself, absorbing and re-radiating the energy of every thought, every broadcast, every flicker of light, and so the void remains full of messages, some we recognize, some we will never understand. Most are unintentional, written by physics instead of purpose. But they're all there, moving quietly between the stars, reminders that even in silence the universe is speaking. We may never hear another voice, we may never know whether our own has been heard, but as long as a light continues to move, as long as radiation crosses the dark, the conversation, if that's what it is, never truly stops. The sun, for all its brightness, is not alone in space. It drifts, like every other star, through the soft matter that fills the Milky Way. Around it, the planets move in their orbits, held by gravity and illuminated by light. But beyond them, the influence of the sun stretches much farther than the reach of its warmth. It creates an invisible boundary, a bubble of charged particles, magnetic fields, and energy that separates our solar system from the interstellar medium. This is the heliosphere, the edge of home. It's not a wall or a shell, but a transition, a frontier between the familiar and the galactic beyond. The heliosphere begins with the solar wind. Every second, the sun releases a steady stream of particles, mostly electrons and protons, from its outer atmosphere. These particles flow outward in all directions, carried by the sun's magnetic field, moving at hundreds of kilometers per second. Near Earth, this wind creates the conditions that shape space weather, stirring the auroras and influencing satellites. But far beyond the planets, where the wind weakens and slows, it meets the thin breath of interstellar gas. The collision of these two flows defines the outer boundary of the solar system, a vast shifting interface between the domain of the sun and the rest of the galaxy. That boundary isn't sharp. It's made of several layers, each shaped by pressure and motion. The solar wind begins supersonic, faster than the speed of the waves that can travel through it. At a certain distance, roughly 80 to 100 times the distance between the Earth and the Sun, it slows down abruptly as it encounters resistance from the interstellar medium. This region is called the termination shock. Beyond it lies the heliosheath, where the solar wind becomes turbulent and mixes with the external flow. At the outermost edge, where the pressure of the solar wind and the interstellar gas balance perfectly, lies the heliopause. Beyond that point, the Sun's influence gives way to the galaxies. The heliopause is the true frontier, the surface where our solar system ends and interstellar space begins. The shape of this boundary is constantly changing. The solar wind isn't uniform. It strengthens and weakens with the Sun's activity cycle, which lasts about 11 years. When the Sun is active, the heliosphere expands, pushing farther into interstellar space. When it's quiet, the heliosphere contracts slightly, allowing the galaxy to press a little closer. The whole system breathes slowly, in and out, in rhythm with the Sun's magnetic heart. For most of history, this frontier was beyond imagination. Even after we began sending spacecraft outward, no one knew where the solar system truly ended. Then, in 2012, Voyager 1 crossed the heliopause. After travelling for 35 years and more than 18 billion kilometres, it entered a region where the density of charged particles changed suddenly, where the direction of magnetic fields shifted, and where the influence of the Sun's wind disappeared. Voyager 1 had left the solar bubble and entered interstellar space. 5 years later, its twin Voyager 2 followed, confirming that the boundary wasn't uniform. It was rough, uneven, and dynamic. The data they sent back revealed that even the edge of home is alive, changing from moment to moment. The interstellar medium beyond the heliopause isn't completely foreign. It's made of the same ingredients, hydrogen, helium, traces of heavier elements, but it behaves differently. The particles move in random directions rather than streaming outward from a central source. The magnetic fields are oriented differently, shaped by the broader flow of the galaxy. The density is higher, the temperature lower, and the particles slower. The Sun moves through this environment like a boat through calm water, its heliosphere forming a wake behind it as it travels around the Milky Way. At the very edge, there may be a bow wave or bow shock, a region where the solar wind and the interstellar medium interact directly, compressing and heating the gas. Whether this feature exists depends on the exact speed of the Sun's motion relative to the surrounding material. Recent measurements suggest that our star moves too slowly to create a full shock wave, producing instead a gentle wave, a ripple in the interstellar medium that follows us as we go. It's a reminder that even in the most remote regions, the forces that shape space act continuously, blending one domain into another without clear separation. The heliosphere protects us. Without it, cosmic rays from distant supernovae and other energetic events would bombard the inner solar system far more intensely. The magnetic fields carried by the solar wind deflect many of these particles, reducing their numbers by orders of magnitude before they can reach Earth. The planets live inside this shield, a cocoon of moving plasma that keeps the galaxy's harsher environment at bay. It's one of the reasons life could develop here, not only because of the Sun's warmth, but because of the invisible barrier that moderates the storm outside. Even so, some cosmic rays do penetrate the heliosphere, their paths twisted and slowed, but not stopped. They provide a constant background of radiation, a reminder that the galaxy's energy reaches us no matter how well we're protected. The boundary of home is porous, a place of exchange rather than isolation. Particles from interstellar space occasionally drift inward, and particles from the Sun escape outward, mixing at the edge. The heliosphere isn't a wall, it's a membrane. Beyond it, the interstellar medium stretches endlessly, the same vast environment that fills the spaces between all stars. The Sun's bubble is one among many. Each star creates its own heliosphere, or astrosphere, shaped by its wind and motion. These bubbles sometimes overlap, sometimes touch, and sometimes drift apart. the galaxy is full of them, like cells in a vast organism, each surrounded by its own boundary, yet all part of the same continuous medium. Between them lies no absolute emptiness, only transition. When we imagine the edge of the solar system, we often think of distance, a line drawn far from the planets, marking the limit of where we've been. But the true edge is not measured in kilometres, it's measured in influence. The heliosphere defines where the sun's power fades, where the balance shifts from the local to the galactic. Beyond it, the interstellar medium takes over, governed by forces larger and older than any single star. To cross that boundary is not to leave home, but to understand its place within something greater. The Voyagers, still travelling outward, continue to send back faint signals, data carried by photons that began their journey almost half a century ago. Those photons, encoded with information about the conditions they measure, cross the heliosphere's layers in reverse, moving inward toward Earth. They remind us that communication continues even across boundaries that seem unreachable. The spacecraft themselves have become extensions of our awareness, small points of understanding carried into the galactic dark. The edge of home is not a static border, but a story of interaction. The solar wind meets the galaxy there. The heat of our star meets the cold of the void. The magnetic fields intertwine, exchange energy, and part again. The entire system moves as the sun orbits the centre of the Milky Way, encountering different regions of interstellar gas along the way. In a few tens of thousands of years, the sun will leave its current cloud, the local interstellar cloud, and enter another, changing the size and shape of the heliosphere once again. The edge of home is always moving, reshaped by both internal and external forces. From a cosmic perspective, the heliosphere is small, a bubble barely noticeable within the galaxy's scale. Yet within it lies everything we know, every planet, every moon, every sign of life. It's a reminder that even in a universe filled with billions of stars, our sense of home is defined by what we can hold close, by the boundaries that give us shelter. Beyond them lies not danger, but continuity, the same physics, the same matter, the same space, simply less familiar. Standing on Earth, looking up at the stars, it's easy to forget that the light we see from them must cross the same boundaries. Every photon that reaches us from the galaxy has passed through the interstellar medium, through the sun's outer defences, through the thin upper layers of our atmosphere, and finally into our eyes. The edge of home isn't just out there in space, it's here too, in the boundary between perception and the unknown. The heliosphere, for all its complexity, is a temporary structure. As the sun evolves, its wind will change. When it becomes a red giant billions of years from now, its atmosphere will expand, engulfing the inner planets and reshaping the boundaries completely. Eventually, when the solar wind fades and the sun becomes a white dwarf, the heliosphere will dissolve, merging with the interstellar medium. The edge of home will vanish, absorbed into the wider flow of the galaxy. What remains will be the atoms and dust that once formed the solar system, carried outward to become part of something new. Even then, the stories won't end. The atoms now resting inside the heliosphere, the air, the oceans, the matter of living things, will one day join the interstellar medium again. They'll drift between solar systems, cool and wait, just like the atoms that once formed the sun and planets before us. The edge of home will move on, but the material of home will stay within the galaxy, part of the endless circulation of matter and light. The sun's bubble, fragile and temporary, is our shelter in the cosmic sea. It marks the place where the warmth of our star meets the cold current of the galaxy, where local order meets universal motion. It's not a wall that separates us from the rest of the Milky Way. It's the surface that connects us to it. Beyond the heliopause, the interstellar medium continues, full of dust, gas, and fields, carrying the echoes of countless other stars. The edge of home, for all its boundaries, is also a bridge. And as the Voyagers continue their silent journey outward, still transmitting, still listening to the faint hum of interstellar space. They carry with them the same message that every photon does, that home is not an isolated island in the dark, but a place within a vast, continuous ocean. The heliosphere is our small ripple in that ocean, our moving mark upon the galactic flow, a reminder that even at the edges we are still connected to everything beyond. There comes a point, if you travel far enough from every star, where the light begins to fade into something softer than dark. It isn't total blackness, not quite. More like a dim grey where starlight is too faint to cast shadows, too weak to reveal distance. This is the stillness between suns. Not a void, not an absence, but a calm so vast that even motion seems to hesitate. Here, the galaxy's energy slows to its quietest state. Matter drifts without purpose. Temperature barely rises above the background of space. The rhythm of everything that once burned, collided, or radiated comes to rest in silence. From the edge of the heliosphere outward, the galaxy becomes almost weightless. The density of particles falls until there may be only a few atoms in a cubic centimetre. Magnetic fields thread through this expanse, thin and slow, carrying weak currents that twist gradually over light years. Cosmic rays pass through, scattered just enough to keep them from travelling in straight lines. Every so often, a photon from a distant star crosses the region, unnoticed by anything capable of seeing it. It keeps moving, unstopped, until its energy fades into the hum of the background. There are no planets here, no orbits, no immediate boundaries, only continuation, a smooth flow of matter and radiation through the quiet framework of the Milky Way. At this distance, even the concept of time changes. There are no regular cycles, no days, no rotations to measure against. Time becomes defined by motion itself, the slow drift of atoms, the gradual cooling of radiation, the patient equilibrium of the interstellar medium. In human terms, nothing happens here. But in the scale of galaxies, this nothingness is a crucial balance. It is the pause between creation and destruction, the resting state that allows everything else to move. Without these calm regions, the energy of the galaxy would be uneven, its structures collapsing faster than they could form. Stillness is what holds it together. Every star sends its influence into this space, just as every supernova sends its shockwaves and every magnetic current its pull. The result is a landscape of subtle gradients, shaped, but never broken. You could cross it for centuries at the speed of a fast-moving spacecraft and see little change. Yet this stillness is not empty. It's the same interstellar medium that fills the rest of the galaxy, just thinner, quieter, more diffuse. The atoms here are the same atoms that once burned in stars, that will one day form new ones. Their sleep is only temporary, part of the long rhythm of motion and rest that defines the Milky Way. It's easy to imagine this space as lonely, but loneliness implies separation, and nothing here is truly separate. Even in silence, connections remain. Magnetic fields link one region to another. Gravitational tides extend far beyond their visible sources. The faint pressure of radiation from distant stars travels endlessly, adding its momentum to the mix. Every atom is part of the galaxy's overall pattern of movement, even if that movement is measured in millimeters per year. The stillness is relative, not absolute. What looks static to us is only motion too slow for our perception. If you could pause here, suspended between suns, you would feel no up or down, no pull or push. You'd be surrounded by a darkness that glows faintly with scattered light, starlight diffused by dust, the soft infrared warmth of distant clouds, the background radiation of the universe itself. The temperature would hover around a few degrees above absolute zero. The silence would be total, not because sound doesn't exist, but because there's no medium dense enough to carry it. Even your own heartbeat would seem alien, the only vibration in a region that has known none for millions of years. The stillness between suns is the galaxy's resting breath. It's where energy redistributes, where the rush of stellar winds slows and the heat of young stars fades into uniformity. When matter leaves a star, blown out by radiation or flung away by gravity, it eventually reaches this space, cooled and stretched until it blends into the general background. Over millions of years, this matter will drift until gravity calls it back again, collecting it into new clouds. The quiet isn't permanent. It's the interval between acts, the long intermission before the next cycle of formation begins. Even the most energetic events in the galaxy, supernovae, gamma-ray bursts, black hole outflows, eventually dissolve into this calm. Their shockwaves lose strength, their light fades, and what remains merges with the cold gas that fills interstellar space. The stillness absorbs everything. It doesn't erase energy, it spreads it thin until no part stands out from the whole. The Milky Way's beauty depends on this balance. Its bright regions can only exist because the dark ones absorb the excess, because the spaces between suns are wide enough to hold the echoes of every explosion and every birth. From Earth, we see the galaxy as a dense band of light, but that brightness is an illusion of perspective. Most of the Milky Way's volume is empty compared to its stars. The glowing disk we observe is only a thin plane where gas and light concentrate. Above and below it stretches a vast halo of diffuse material, ancient gas, dark matter, and stray stars. This halo connects to the spaces between systems, forming a continuous environment that fills every gap. When astronomers map the galaxy in X-rays or radio waves, they see this hidden structure: bubbles, filaments, and voids that span thousands of light years. The stillness between suns is not isolated. It's woven into the galaxy's greater pattern. Within this calm, individual atoms follow paths set by both chance and law. Some drift through magnetic fields, spiraling gently as they go. Others move in straight lines for years before colliding with anything. Occasionally, a cosmic ray passes through, transferring a small amount of energy, ionizing an atom, creating a fleeting spark of interaction. The result is a kind of background activity, subtle, statistical, but never absent. On average, an atom in these regions might collide with another only once every few thousand years. Between those moments, it simply moves, unbothered, unchanged. This quiet movement has consequences. It allows molecules to survive for long periods without disruption, giving time for complex chemistry to occur. It lets magnetic structures persist, undisturbed by turbulence. It provides the cooling needed for dense clouds to eventually form. The stillness is creative in its own way, not through action, but through the conditions it maintains. It's the slow foundation upon which every act of creation in the galaxy depends. In the spaces between solar systems, radiation pressure from many stars overlaps, creating a soft, collective glow. It's too faint for human eyes, but instruments can detect it, a diffuse background of starlight reflected by dust. It gives the galaxy an inner luminescence, a reminder that even its emptiest regions are touched by light. The stillness doesn't mean darkness, it means equilibrium, where illumination and shadow balance perfectly. For any civilization that ventures beyond its own star, the stillness between suns will be both barrier and sanctuary. The vast distances mean isolation, but also safety from heat, radiation, and chaos. Spacefarers crossing this gulf would see stars as fixed points, unmoving over lifetimes. The universe would appear frozen, yet they would still be moving, carried along by the sun's orbit through the Milky Way, part of the galaxy's slow rotation. Even in apparent stillness, motion continues. The galaxy itself turns, and with it, everything inside. The stillness has its own sound if sound could exist here. It would be a steady hum of background radiation, the quiet vibration of the cosmic microwave background, the faint hiss of charged particles drifting through magnetic fields. Instruments can translate that energy into signals we can hear, a reminder that silence is relative, that even in the emptiest places the universe continues to speak in frequencies too subtle for our ears. Sometimes astronomers detect mysterious radio bursts or faint repeating signals coming from distant regions of the galaxy. Most turn out to be natural, magnetars flaring, pulsars spinning, jets from black holes flickering in rhythm. But every new discovery begins the same way, with a whisper from the void, a reminder that stillness does not mean absence. The galaxy's calm is alive with processes too slow for human time, too vast for human distance. On a galactic scale, the stillness between suns is a stabilizing force. It provides room for motion without chaos, time for cycles to unfold, and balance between extremes. Without it, energy would crowd, light would blind, and the delicate structure of the Milky Way would collapse. It's the empty space that gives form to the filled one, the silence that makes sound meaningful. Between stars, the universe maintains its continuity by allowing vastness to breathe. And within that vastness, everything that exists, dust, gas, light, and life, shares the same destiny: to move outward, to slow, to rest, and eventually to return. The stillness between suns is not an ending, but a rhythm. Every particle that sleeps there will one day wake again, drawn into new gravity wells, heated by new stars, carried into new systems. The calm holds the seeds of motion. The dark contains the source of light. From our small planet, orbiting one star among hundreds of billions, it's easy to forget that this quiet reaches everywhere. The peace we associate with the night sky, that deep contemplative stillness, is the echo of what fills most of the galaxy. The spaces between suns are not far away. They begin just beyond the reach of our own. We are surrounded by them, sustained by them, part of them. The Milky Way's serenity is the background against which all life and light unfold. And so, when you look up at the stars and see the thin silver band of our galaxy stretched across the dark, you're not only seeing the brightness of suns, you're seeing the stillness that holds them apart. The quiet fabric that lets them exist without colliding, that lets energy disperse and reform, that gives the galaxy its balance. The calm between the stars is not empty space. It's the heartbeat of the Milky Way, slow and steady, marking the rhythm of everything that has ever been born and everything that will ever be again.